Have you ever wondered why so many things in the universe only move in one direction? Hello there, and welcome to The Sleepy Scientist. It is good to have you here tonight as you wind down, settle in, and let the day soften around the edges. This video drifts gently through the idea of irreversibility, the quiet one-way behavior that shapes so much of the world around you. Before we begin, I'd love to know where you happen to be listening from this evening. If you enjoy these calming explorations, a like and a subscribe would really help the channel continue to grow. And to everyone who is already subscribed, thank you so much for being here. Feel free to tap the notification bell as well, just so you do not miss the next upload when it arrives. And hopefully this video is relaxing enough to help you drift off, though there is always the small chance it might be a little too interesting, in which case at least you will fall asleep a tiny bit wiser. So let your shoulders loosen, let your thoughts spread out a little, and settle into a quiet pace. Because tonight we are exploring the gentle truth that many changes in the universe cannot be undone once they have happened. And that raises a simple question to guide the journey ahead. What makes the forward flow of time, and all the irreversible things within it, such a natural part of the universe? Irreversibility shapes the world in ways that are easy to miss but impossible to escape. It appears in the warmth that drifts out of a cooling drink, in colours that mix and never separate again, in the slow fading of energy from every star, and in the tiny details of events that disappear as moments pass. Even though the deepest rules of physics allow processes to run either way, the world you experience does not behave like that. It leans forward, step by step, with each change settling into place. This quiet imbalance between what is possible in theory and what happens in practice is at the heart of tonight's journey. The smallest particles can move in patterns that, in principle, could reverse. Yet when countless particles gather into the objects and environments that make up daily life, something shifts. The complexity becomes too great, the odds too overwhelming, and the universe's direction becomes unmistakable. Things blend, things cool, things age, things spread, and once they do, they rarely return. As you relax into the slow rhythm of this exploration, you will hear how processes gain their one-way nature, how the universe gradually forgets its past, and how time's forward push emerges from simple statistical truths rather than anything mystical or dramatic. It is a story woven through heat, motion, memory, energy, and chance, and each part of it reveals another layer of why the world feels so settled in its direction. So let the pace remain slow, the ideas gentle, and the explanations soft around the edges. Because irreversibility is not just a concept in physics, it is the quiet foundation beneath the flow of every moment you move through. And as we begin, consider this. If time seems determined to move forward, what hidden rules give it that steady push? When you look at the world around you, it is easy to forget how many of its changes quietly move in only one direction. A block of ice melts into water and never refreezes itself on a warm day. A splash of milk swirls through a cup of coffee and never drifts back into a neat white puddle at the bottom. A dropped glass shatters into many pieces and never leaps back together, no matter how long you stare at the floor. These moments feel so normal that you rarely question them. They simply happen, and once they do, the original state is gone. Yet beneath these familiar events lies something deeper about the way nature works. Something that shapes the flow of time and forms the backbone of irreversibility. You might imagine that the reason these things happen only once is because of some built-in barrier or hidden rule prohibiting them from going backward. But the truth is more surprising. At the smallest level, the rules that govern the motion of atoms and molecules do not actually care about direction. If you could zoom down to the tiniest details, the laws that move particles forward in time could, in principle, move them in reverse just as easily. Nothing at that scale truly forces the universe to choose one way over the other, and yet the world you interact with every day behaves as if reverse is simply not an option. That is the puzzle at the heart of irreversibility. Nature's building blocks allow reversals, but everything built from them does not. A single ice cube does not melt because its molecules forget how to form a solid. It melts because the warmth from the environment jostles those molecules, nudging them into a looser, more flexible arrangement. To reverse that process perfectly, every one of those molecules would need to retrace its exact steps. Each one would have to collide with the same neighbours, at the same angles, with the same precise energies as before, all at the same moment, and not just a few molecules but unbelievably large numbers of them. You would need to coordinate far more particles than there are grains of sand on the planet. The chance of that happening naturally is so tiny that it might as well be zero. The universe is not refusing to refreeze your ice cube. It simply does not bother arranging the unimaginably precise chain of coincidences required to put everything back. This same idea appears in something as simple as mixing. When you pour juice into water, the colours do not remain separated. They drift and blend until the whole drink looks uniform. To undo that mixture, every particle of juice would need to gather itself back together in just the right place, at just the right moment, without stirring everything else in the process. The number of possible scrambled arrangements is so overwhelmingly larger than the number of separated arrangements that the universe almost always ends up with a blended version. In a sense, it is not that nature dislikes order, it is just that disorder is the easiest outcome to reach, because there are countless more ways for things to be mixed than to be tidy. Breaking something follows the same logic. When a glass slips from your hand, it hits the ground, vibrates, cracks, and flings pieces outward. All of those fragments fly off in a chaotic dance influenced by tiny imperfections, air currents, bumps in the surface, and random fluctuations in the way the material gives way. For it to unbreak, every shard would need to reverse that chaotic path. They would need to spin backwards through the air, match their edges perfectly, and fuse with the exact energy that held them together before. It is not that a broken glass cannot theoretically reform itself. It is that the universe almost never produces the chain of events needed to make such a reversal happen. That is the quiet heart of irreversibility. It is not a strict rule laid down by some external force. It is a matter of overwhelming probability. There are many, many more paths leading toward mixed states, melted states, scattered states, and broken states than toward the precise arrangements needed to undo them. As systems grow larger and more complex, the difference becomes enormous. You could think of it like trying to shuffle a deck of cards until every card returns to the exact order it started in. It is not impossible. It is just that the number of other possible arrangements grows so vast that waiting for the original order to appear again would take longer than the lifetime of the universe. Nature does not forbid reversals. It simply prefers the paths that are easy to reach. This gentle preference appears everywhere. When heat leaves a warm object and spreads into the surrounding air, it does not gather itself back again. The warm and cool regions smooth themselves out because there are more ways for energy to be spread than concentrated. When two gases mix, they drift into a shared space because the number of possible mixed arrangements dwarfs the number of separated ones. When a pattern of neatly arranged molecules is disturbed by a small nudge, it rarely flips back to its original structure. Not because it is forbidden to do so, but because the original structure is just one arrangement among a staggering number of possibilities. The universe is not making a philosophical choice. It is simply taking the most statistically accessible road. Irreversibility, then, is not a sharp line you can point to. It is a soft, steady drift towards states that are easier for the universe to reach. When many particles interact, their exact movements become impossible to track. Tiny differences grow, details blur, information about precisely how things used to be gets dispersed into countless degrees of freedom, and the more those details spread, the harder it becomes to gather them again. What once was a crisp, tidy arrangement dissolves into something with far more possible forms, and the universe, indifferent and quiet, drifts toward whichever form is easiest to fall into. You can think of this tendency as the universe's gentle leaning, a leaning toward mixing rather than unmixing, softening rather than sharpening, scattering rather than gathering. It is not a conscious preference or a cosmic rule book. It is simply that at any given moment there are far more accessible outcomes on the side of disorder than on the side of precise order. The world follows the broad slope of possibility, not because it must, but because it is overwhelmingly likely to do so. This is why irreversibility is so deeply woven into the feel of everyday life. When things change, they tend to change in ways that are easier, not harder. When processes unfold, they spread their influence outward. When something breaks, the pieces scatter into countless patterns, and when heat or motion disperses, it does so in a way that blends the details into something smoother. The universe drifts toward the broad landscape of states that require no tight coordination, no perfect timing, no miraculous alignment of microscopic steps. And although the smallest particles beneath everything can run their motions in reverse just as easily as forward, the world you live in does not follow those reversible possibilities. It follows the paths that are plentiful, the ones that require no special coincidences. That is the gentle idea at the foundation of one-way physics, not a strict rule enforced by the cosmos, but a quiet tug toward the simplest, most probable outcomes. Irreversibility is what happens when the universe takes the path of least resistance, one tiny movement at a time, until the direction becomes unmistakable. Time is something you move through so constantly that you hardly ever stop to question what it really is. You feel it as a flow, a steady push carrying you from one moment to the next. You sense it as a sequence of events, a line running from what has already happened toward what has not yet occurred. You organize your life around this flow. You wake, you eat, you work, you rest, and you drift toward the end of the day as naturally as breathing. But behind this familiar feeling lies one of the most striking examples of irreversibility. Time does not run in loops. It does not pause and restart, and no matter what you do, it does not reverse itself. This quiet, unwavering direction is known as the arrow of time. One of the most intuitive signs of this arrow is memory. You remember the past, but you cannot remember the future. You can recall what you had for breakfast last week, the sound of a conversation you once had, or the feel of a place you visited years ago. But you cannot wake up and remember something that has not yet happened. Your brain forms memories by changing itself in small ways, strengthening some connections and weakening others. Those changes are physical processes involving energy moving from one pattern to another. Once that rearrangement takes place, the previous state is gone. To reverse a memory, you would need to unchange every tiny step your brain took to make it, right down to the movement of individual molecules. As impossible as that sounds, it reflects a deeper truth. Memory itself is built on irreversibility. Your brain records what has already happened because the physical processes involved only run forward. Clocks, too, mark time's direction. A clock does not simply display numbers. It measures the steady progression of physical events. Springs unwind, pendulums swing, quartz crystals vibrate, atoms shift through precise cycles of energy. Each of these changes follows a natural sequence that cannot perfectly reverse itself. The clock moves one tick at a time, not because the gears refuse to turn backward, but because the processes driving them rely on energy flowing from one state to another. Once that energy shifts, the event that produced it becomes fixed in place. Even the most accurate atomic clocks, which can measure the passing of time with astonishing precision, depend on transitions that unfold in one direction only. They do not hint at time's arrow, they embody it. You can see the same pattern in chemical reactions. When two substances react, they often release energy into the environment. That energy disperses, becoming more spread out and less available than before. For the reaction to run backward, that same energy would need to gather itself again in exactly the right form and return to the precise molecules that released it. This is not forbidden by any law of nature. It is merely extraordinarily unlikely. The forward direction is easy. The backward direction requires perfect coordination, and so chemistry, like memory and clocks, follows the path most available to it. Heat also reveals time's direction. If you hold something warm in your hand, you feel the energy drifting outward into the surrounding air. After a while, the warmth fades. It never suddenly returns. Heat moves from warm places to cooler places, because there are countless more ways for energy to be spread out than concentrated. To reverse that flow, all the tiny movements of the surrounding air molecules would need to align perfectly to send the warmth back into the object. It could happen in theory, but the odds of that happening at random are so small that the universe will almost certainly never produce it. This gentle spreading of energy creates one of the most important arrows of time. Wherever heat flows, time flows with it. In your daily life, you rely on this directionality in ways you might not even notice. You trust that the cup of tea you set aside will cool, rather than spontaneously reheat itself. You expect your footsteps to leave impressions in soft sand, not the reverse. You depend on cause leading to effect, not effect casually leading back to cause. You would find it unsettling if events unfolded in reverse, not because it is logically impossible, but because it never happens. The arrow of time sets the rhythm of existence, turning moments into memories and possibilities into outcomes. At the deepest level, though, this arrow is puzzling. The fundamental laws that govern particles do not care about past or future. If you were somehow able to reverse the motion of every single particle in a system, the laws of physics would allow it to retrace its path precisely. Yet whenever you scale up from individual particles to the objects and experiences of daily life, the universe begins to behave differently. The details become too numerous to track. Small variations amplify. Information about earlier states spreads out, dissolving into the environment, and as soon as those details blur, the possibility of a perfect reversal becomes effectively unreachable. This is why time feels like a one-way journey. The underlying rules do not force events to move forward. Instead, the overwhelming complexity of large systems ensures that forward is the only direction that can occur naturally. It is like watching a film of a glass shattering. If you ran that film backwards and the shards leapt into the air, spinning toward each other and reforming seamlessly into a perfect glass, you would instinctively know something was wrong. Not because the backward motion breaks any physical rule, but because it demands an alignment so unlikely that real life never produces it. The glass shatters easily. It unshatters only under careful control or imagination. In a quiet way, the arrow of time is not a separate force. It is the cumulative effect of countless irreversible processes, every reaction that releases energy, every warm object that cools, every mixture that blends, every structure that degrades slightly over time. All of these tiny movements combine into a single overarching sense of direction. The world tips subtly but firmly towards states that are easier to reach than reverse. And because of that, time feels as if it is carried along with the flow. This forward drift underpins your ability to navigate life. You rely on the idea that tomorrow follows today, that outcomes grow from causes, and that the world does not arbitrarily swap its order. Without time's arrow, everything would feel uncertain, unpredictable, or even incomprehensible. Yet with it, the flow of events becomes something you can trust, something that gives structure to your experience. Even when days feel long or weeks blur together, the underlying sense of direction remains the same. You moved from where you were to where you are, and you will move from here to whatever comes next. The arrow of time, then, is not imposed on the universe by any external rule. It emerges naturally from the countless irreversible events unfolding around you and within you. It is the quiet sum of energy dispersing, reactions completing, information spreading, and complexity increasing. The world leans forward because forward is simply the easiest way for all its pieces to move, and as long as that continues, time will feel like a river that never flows upstream, guiding every moment gently but firmly toward the next. Entropy is one of those words that appears in science often enough to sound familiar, yet remains vague enough to feel slightly mysterious. It tends to be described in abstract terms that make it seem like a hidden force running behind the scenes. But at its heart, entropy is much simpler. It is the quiet tendency of things to spread out, blend together, and smooth themselves over. When you hear the word entropy, you can think of it as the universe's habit of evening things out. Warmth spreads until temperatures match. Colours swirl until they blend. Gases drift until they fill the space available. Little by little, the sharp edges between different states soften, and the world becomes more uniform. This softening is not a rule that objects must obey. It is simply the easiest path for them to take. You can imagine this smoothing in something as simple as scent. If you open a bottle of perfume in a still room, the fragrance does not stay in one corner. It finds its way throughout the space, carried by the gentle jostling of air molecules bumping into one another. Nothing instructs the scent to spread. It spreads because there are many more ways for those perfume molecules to occupy a large volume of air than to stay clustered together. The initial concentrated state is special and unlikely. The diffuse state is ordinary and easy to reach. Entropy is the measure of this shift from special to ordinary, from concentrated to spread out. The same idea appears whenever something warm cools down. If you place your hand near a warm mug, you feel a gentle drift of heat leaving it. The warmth does not remain neatly inside the liquid. It flows outward, dissolving into the surrounding air until everything reaches an even temperature. In principle, those tiny movements of energy could all reverse themselves. The warmth could gather itself back into the mug, making it hotter than before. But the chance of all those random motions lining up in reverse at the same moment is unimaginably small. The warm mug does not cool down because the universe dislikes warmth. It cools down because spreading the energy around is far easier than collecting it again. Entropy, then, is not about chaos or disorder in the dramatic sense. It is about the number of ways things can be arranged. A neat, tidy arrangement has only a few possible configurations. A spread-out one has countless possibilities. Think of a deck of cards. There are only a few ways to organize it into perfect numerical order, but there are enormous numbers of ways to shuffle it. If you shuffle the deck randomly, you are far more likely to end up with a jumbled arrangement than a sorted one. Nature behaves the same way. It drifts toward the states that are easy to reach, simply because there are so many more of them. This smoothing also appears in liquids. If you pour a little syrup into water, the colours and textures blend gradually. First you see swirling tendrils, then soft clouds, and eventually a completely uniform mixture. You can stir it to speed the process up, but even without stirring, the blending would still happen. The molecules move and collide, and with each collision there are far more outcomes that leave them mixed than unmixed. Entropy is this gentle leaning toward blending. It shows up whenever sharp boundaries fade and distinct states soften into something more uniform. In daily life, you feel entropy most clearly in warmth. Heat is a restless traveller. It always seeks balance. A warm room leaks energy to a cold night. A hot spoon left on the counter loses its heat to the air. Even your own body radiates warmth constantly, which is why stepping outside in winter makes that warmth vanish quickly. All of this happens because the energy inside warm objects is in a concentrated form. As soon as it has the chance to spread, it flows outward. The environment around it absorbs the energy, because there are so many more ways for that energy to be diffused into far more particles than held inside a few. This behavior gives rise to the feeling of before and after. Before the mug was warm, after it cooled. Before the liquids were separate. After they blended. Before the scent stayed inside the bottle. After it drifted around the room. These changes rely on entropy because entropy gives direction to the unfolding of events. Once energy spreads or once molecules blend, the original state becomes something that requires an impossibly precise alignment to recreate. You experience this as the simple fact that moments pass. Things that were once true become part of the past. Things that are now true become your current experience, and things that will be true wait in the future. Entropy sets the stage for that flow. Even the air around you carries this idea quietly. Air molecules are constantly moving, bouncing, and drifting. Their collisions are unpredictable on their own, but when you consider the enormous number of them, a pattern emerges. They always find ways to spread energy evenly. They always soften sharp differences in temperature or concentration. The overall behavior becomes so predictable that you can rely on it completely. You know a warm room will cool, you know a cold drink will warm up, you know steam will dissipate, and you know that none of those processes will reverse by themselves. Entropy does not stop at mixing or cooling. It appears whenever a system moves toward a state that requires no special coordination. A sandcastle, for instance, is a very specific arrangement of grains. Wind, waves, and footsteps can disrupt it in countless ways. To build it again, every grain would need to be placed precisely, one by one. There are vast numbers of ways for the castle to fall apart and only a tiny number of ways for it to take its original shape, so it erodes easily and rebuilds only with effort. Entropy favours the simple, the blended, the widely spread, and the balanced. This does not mean the universe is heading towards some dramatic decline. It simply means that systems tend to seek states that are easier to occupy. When something spreads, it does so because nothing is preventing the spread and because the spread out state has far more possibilities. When something cools, it does so because the surrounding environment offers countless paths for the energy to disperse. Entropy is not a destructive force. It is a guide to what is most likely to happen. You can see this at work on much larger scales too. Stars shine by converting concentrated energy into light and heat, which then travel outward into space. Over time, these stars cool as that concentrated energy spreads across vast distances. The light that reaches your eyes tonight may have travelled for thousands of years, drifting further and further from its source, becoming more dilute as it goes. That spreading is entropy acting on a cosmic level. It is the same idea that cools your tea or mixes the colours in a glass of water, just playing out on a grander scale. Entropy gives the universe its sense of direction not because it forces anything, but because it makes some states so vastly more common than others. The world moves from concentrated to dispersed, from separated to mixed, from uneven to even, because those states are simply easier to reach. The original arrangements are not impossible to recreate. They are just extraordinarily unlikely. And that is enough for the universe to lean forward, smoothing and spreading its way through every moment. As you move through your own day, you experience these shifts as ordinary events. A warm surface cools, a scent drifts, a mixture blends. Each of these moments is an expression of entropy gently nudging the world toward balance. And even though the causes are microscopic, the effects shape your understanding of time itself. Entropy creates the gentle difference between what was true a moment ago and what is true now. It gives you a sense of the world's progression, the quiet unfolding of change, and the feeling that the future will always grow out of the present, never the other way around. In that way, entropy is not just a scientific concept, it is a soft rhythm beneath everything you see, guiding the spread of energy, the blending of matter, and the subtle drift that turns moments into memories. Heat is something you feel long before you ever think about it. You sense it in your hands when you hold a warm drink, in the air when sunlight drifts through a window, and in the slow fading of warmth from your skin on a cold evening. It seems simple on the surface. Warm things cool down, cool things warm up, and given enough time everything settles somewhere in the middle. But beneath that everyday experience lies one of the clearest examples of irreversibility. Heat moves from warmer places to colder ones with a quiet certainty that never seems to falter. No matter how long you wait, the warmth from a cup of tea will not suddenly rush back into the liquid and make it hot again. The universe has a gentle preference, and that preference points in one direction. To understand why, imagine looking at heat not as a single thing, but as the restless motion of countless tiny particles. When something feels warm, what you're truly sensing is the rapid movement of the molecules inside it. They are jostling, vibrating, and interacting far more vigorously than the molecules in something cooler. When these two sets of molecules meet, the energetic ones bump into the slower ones, passing some of their energy along. Each collision changes things slightly. The warm object loses a little of its energy, and the cooler surroundings gain a little. Over time, those countless tiny interactions spread the energy evenly, smoothing out the difference between warm and cold. From your perspective, the warm thing cools down, and the cooler environment warms up. Reversing that flow would require something astonishing. Every single particle in the environment would need to give back exactly the right amount of energy at exactly the right moment, sending the warmth back into the object instead of absorbing it. And not just a few particles. You would need a perfectly coordinated reversal involving numbers so large they are difficult to imagine. There are far more molecules in a cup of tea than there are stars in the Milky Way galaxy. Trying to get all of them to cooperate in that kind of precise backward dance is beyond improbable. It is like asking every grain of sand on an entire beach to arrange itself into a perfect castle spontaneously. Not impossible in theory, but so unlikely that the universe will never produce it naturally. This impossibility of reversal is what ties heat flow to the arrow of time. Heat drifting outward marks a clear before and after. Before, the object was warm and the surroundings were cool. After, the warmth has spread and the difference has faded. That spreading cannot undo itself without a level of coordination that the random motion of particles simply does not provide. Time feels as though it is moving forward because certain processes, like the movement of heat, only run one way. Once energy is drifted outward, the earlier state becomes something that exists only in memory or imagination. This smoothing effect is easy to see in little everyday moments. Think about taking a freshly baked loaf of bread out of the oven. At first, it radiates heat into the room. The warmth flows into the air, into your hands, and into anything nearby. Over time, the loaf cools, becoming closer in temperature to everything around it. You do not expect the room to become noticeably cooler as the bread reheats itself. You simply know that the direction of heat flow is fixed. You also feel it when you step into a cold swimming pool. Your body's warmth rushes into the water. The water does not suddenly surge in temperature while your body becomes even warmer. The movement goes one way, because that way is the easiest path for countless tiny interactions to follow. A helpful way to visualize this is to imagine heat as a crowd of restless children in a playground. When they are clustered in one corner, the energy is concentrated. They're bouncing around, bumping into each other, filling the space with noise and motion. But if you open the gates to the rest of the playground, the children spread out. They do not stay packed in the same corner. They naturally wander into the open space because there are far more ways for them to be dispersed than squashed together. Heat behaves the same way. It rushes toward open possibilities. It spreads not because it prefers to, but because spreading requires no special coordination. Concentration, on the other hand, requires maintaining a very specific arrangement, something nature rarely provides by accident. This natural redistribution gives the universe a kind of thermal memory. A warm object cools, and once it does, the original arrangement of energetic particles is lost. Trying to recreate the earlier state would mean putting every tiny part of the system back where it was, with just the right amount of energy. Thermal history fades because the details dissolve into the environment. It is this dissolving of details that gives time much of its one-way feel. When energy spreads out, the universe effectively forgets how things used to be. And once forgotten, the earlier state becomes impossible to rebuild without enormous effort. Heat flow also has a calming reliability that makes the world predictable. You know that a leftover meal cools once it leaves the oven. You know that the metal buckle of a car seat becomes dangerously hot in the sun and then slowly gives its heat back to the air. Even something as simple as touching your forehead with the back of your hand relies on this principle. The direction of heat flow tells you whether you have a fever. Warm moves to cooler, never the other way around. The certainty of that flow makes countless small tasks possible. Without it, temperature would behave erratically and the world would feel much less stable. That gentle consistency reveals something subtle about the universe. Left alone, energy spreads out rather than piling up. Temperature differences fade instead of sharpening. Sharp contrasts soften over time. This is not forced by any external rule. It is simply what happens when vast numbers of particles interact freely. In a way, the universe moves toward thermal calm. The sharp differences mellow. The concentrated heat levels out. The chaotic dance of tiny collisions results, on the large scale, in smooth, predictable behavior. You can imagine an extreme example to make this clear. Suppose you place a hot metal rod in an enormous block of ice. At first, the rod is blazing hot and the ice is frigid. Over time, the heat from the rod melts the ice around it. The water warms and the rod cools. Eventually, if you waited long enough, the entire system would reach a common temperature somewhere between the two extremes. That final state is incredibly easy for the universe to reach, because the number of possible ways the energy can be spread is enormous. In contrast, the initial state was tightly arranged, lots of energy in one place and very little in the other. Recreating that arrangement naturally would require reversing the direction of millions upon millions of collisions. It simply will not happen. This connection between heat flow and the arrow of time is fundamental. Every cooling object, every mixing of warm and cold air, every night breeze carrying warmth away from the ground, every cup of coffee left unattended, all of these contribute to the sense that time goes in only one direction. You never see heat rushing from cold air into your drink to reheat it. You never watch a cooled object gather energy from its surroundings in just the right pattern to warm itself. These things do not occur because the universe does not arrange the necessary coincidences. Instead, it follows the broad, easy path of spreading. And in that simple, repeated action, time gains its direction. The universe smooths out temperature differences, and in doing so, it smooths out the distinction between past and present. Before, the warmth was concentrated. After, it has dispersed. This gradual shift is so reliable that you can build your sense of time around it without even thinking. The flow of heat, then, is one of the clearest windows into the nature of irreversibility. It shows how microscopic chaos results in macroscopic order. It shows how countless random collisions produce an overall drift that feels steady and predictable. And it shows why the world leans forward, from concentrated to dispersed, from uneven to balanced, from warm to cool. Every warm object cooling, every cold surface warming, and every pocket of heat settling into its surroundings is a small but certain step in one direction. A direction you recognize instinctively as the passage of time. Mixing is one of the simplest and most familiar examples of irreversibility, and because you see it so often, it is easy to overlook how remarkable it truly is. You stir sugar into tea and it dissolves. You pour milk into coffee and it swirls into soft clouds before settling into one smooth colour. You add a drop of food colouring to water and watch it stretch into delicate ribbons before eventually vanishing into a perfectly even shade. These little moments happen so smoothly, so automatically that it can feel as if nature prefers the mixed version of things. In a sense, it does. Not because mixing is better or more natural, but because there are far more ways for the particles in a mixture to be spread out than neatly separated. Imagine two liquids sitting side by side in a glass. One is coloured, the other is clear. At first they may form a sharp boundary, but as soon as even a few molecules cross that line, the boundary begins to blur. Every jostle, every bump, every tiny collision pushes more molecules from one region into the other. Once that process begins, it does not stop. Those molecules wander further and further until the distinction between the two liquids fades completely. This happens not because the liquids are trying to mix, but because the motion of their molecules constantly explores every possible arrangement. And mixed arrangements outnumber separated ones by a staggering amount. You can picture this more easily by imagining a jar filled with red and white beads. If you carefully arrange all the red beads on one side and the white on the other, you have created a very special, very precise arrangement. But as soon as you shake the jar lightly, the beads tumble and bounce, and the colours start to mingle. If you keep shaking, the mixture becomes more uniform. There are countless ways for the beads to be jumbled together, but only a few ways to keep them neatly sorted. The mixed state is not more meaningful or more correct. It is just overwhelmingly more likely. Liquids behave the same way. The swirling patterns you see during mixing are temporary moments where the system is moving toward this massively larger space of possibilities. Once fully mixed, the liquid does not spontaneously separate again, not because separation is forbidden, but because it is incredibly improbable. For the mixture to unmix, every molecule would need to move to precisely the right location, coordinating with astonishing accuracy across vast numbers of particles. Even a small cup of liquid contains more molecules than there are stars in the observable universe. Asking all of them to retrace their paths perfectly is asking for a miracle of coordination that nature has no reason to provide. This is why the process of stirring is so one-sided. When you stir, you shepherd the liquid into one of the countless mix configurations. Your movement gives the molecules a little push, encouraging them to explore more of the available arrangements. Once they settle into a mixed state, the system has reached a place where there are so many possible microscopic patterns that it remains there. Nothing in the chaotic motion of molecules will arrange them back into the special, tidy pattern they once had. You could stir for a second or stir for an hour. The direction is always the same. The liquid will never quietly reverse itself. Order in this sense is special. It represents a tiny island in a vast sea of possibilities. A perfectly separated mixture is a rare, precise arrangement. A mixed one is just about everything else. Disorder, as it is often called, is not a negative word. It simply means that the particles can arrange themselves in far more ways. And because nature tends to drift toward whatever has the most options, mixed states are the ones you see most often. The universe is not making a moral decision. It is not choosing chaos over structure. It is simply following the gentle slope of probability. This understanding brings a strange sort of comfort. When you watch two substances blend, you are witnessing a universal tendency toward balance. Sharp differences soften, concentrated pockets diffuse, and edges smooth themselves out. The process is calm, predictable, and reliable. You do not expect the dyes in a painting's water jar to suddenly form stripes again. You do not expect the cream in your coffee to reappear as a pale puddle at the bottom. You know these things will not happen because you understand, even without thinking about it, that the world naturally moves toward mixtures rather than away from them. The ease of mixing also appears in gases. If you release compressed air into a room, it spreads out into the available space almost instantly. You never see the reverse, a room spontaneously gathering all its air into a single corner. There are far more ways for the air to be evenly distributed than concentrated. Similarly, when you exhale, the warm breath carries carbon dioxide into the surrounding atmosphere. It does not linger in a neat cloud. It disperses because that state has countless more arrangements than the tightly packed one you released it from. This tendency toward blending plays a quiet role in shaping your sense of time. You recognize the direction of events because mixing does not run backward. Before, the milk floated in a distinct layer. After, it blended seamlessly. Before, the food colouring formed a clear droplet. After, it filled the whole glass. These changes unfold smoothly and permanently. Once mixed, the earlier states become part of the past, something the universe will not naturally recreate. This creates a feeling of after that is as much a part of your experience as the ticking of a clock. Even solid materials show this tendency, although more slowly. Over long periods, atoms in metals, rocks, or crystals drift and rearrange themselves in ways that gradually soften sharp boundaries. The process is far more subtle than swirling liquids, but the underlying principle is the same. Given enough time and enough tiny movements, systems drift toward states with more possible arrangements. Differences fade. Patterns become gentler. Order shifts gently toward a state where more configurations are available. Understanding why mixing happens so easily adds a layer of calm predictability to the world. You can rely on this behavior. You know that stirring something once is enough to commit it to a mixed state. You know that once two substances blend, that mixture will not reverse itself. You know that diffusion, whether it is heat, scent, or colour, follows a soft one-way path. The world tends to spread things out because spreading allows an enormous variety of microscopic patterns, while separation allows only a few. So when you watch two colours swirl into each other, or when you see a spoonful of sugar vanish into a cup of tea, you're witnessing one of the simplest expressions of entropy's gentle pull. Mixing is not a forceful process. It is a natural slide into states that are easier to reach than avoid. And in that slide you can see the quiet preference of the universe, a leaning toward balance, blending, and the countless arrangements that lie beyond the narrow island of perfect order. In many ways, the universe behaves like a place with an imperfect memory, not the sort of memory that recalls events in the way a person might, but something deeper and more structural. As time moves forward, the fine details of how things once were gradually dissolve. The world keeps the broad strokes. A glass fell and shattered, a cup of tea cooled, a scent drifted through the air. But the exact details that made those moments unique slip away. This fading of detail is not just a poetic idea. It is one of the most important reasons the universe behaves irreversibly. Once the smallest pieces of information are lost, there is no path back to the precise conditions of the past. Imagine a footprint left in soft sand. At first the shape is clear, the edges are crisp. You can see the pressure points from the heel, the arch, and the toes. For a moment, the sand records exactly where the foot was and how it moved. But as time passes, the wind stirs grains, the air shifts, and tiny movements smooth the edges. After a little while, the footprint becomes softer, rounder, less distinct. Eventually it blends into the surrounding sand until it is no longer recognizable. The sand has not erased the footprint intentionally. The countless small interactions taking place at its surface have simply overwritten the details. The same thing happens on a microscopic scale throughout the universe. Tiny collisions, vibrations, and fluctuations constantly rearrange matter and energy, washing out the fine-grained structure of past events. This gradual loss of information is what prevents the universe from perfectly rewinding. If you wanted to reverse a simple process, say, a cube of ink dissolving in a glass of water, you would need every single molecule to retrace its exact path back through the mixture. Each one would have to move back along the same route, colliding with the same neighbours, at the same times, with the same energies. The problem is not that physics disallows such a reversal. It is that the details required to produce it have been scattered so widely that they no longer exist in a recoverable form. The system has forgotten too much. Once the details are lost, the past becomes something the universe can no longer reconstruct. You can still describe the broad pattern of what happened. The ink spread, the water changed colour, the mixture became uniform. But you cannot recover the specific route each molecule took along the way. Those details have dissolved into the wider motion of the system. This is the heart of irreversibility. It is not simply that processes move forward. It is that the information needed to move backward melts away. This forgetting happens in almost every natural process. Heat spreading from a warm object into a cool room carries with it the memory of where the energy once was, but only in the most general sense. You can say the object was warm and now it is cooler. You can say the room was cool and now it is slightly warmer, but the exact pattern of microscopic energy transfers, the tiny collisions that gave heat its direction, becomes impossible to track. Each collision is influenced by countless factors, from the air's motion to the positions of surrounding molecules. The details vanish into the vast number of possible microscopic states. The system forgets where it came from, and in forgetting, loses the ability to return there. You see the same behaviour in the world around you. When a pile of leaves scatters in the wind, you can tell roughly where the pile might have been, but you cannot determine where each leaf originally sat. When a wave washes across a beach, it smooths footprints and sand patterns. You can tell that the tide rose and fell, but not how each grain moved. When fog rolls across a field, it absorbs scents and traces of warmth from the ground, dispersing them into a wide, indistinct cloud. Each of these moments shows how the universe tends to overwrite detail with broader, more uniform patterns. The narrow, specific configurations become lost among a vast number of possibilities. This leads to a quiet but profound idea. The present contains less information about the past than the past once contained about the present. Every change sands away a little more of the detail. The world keeps the general outline. Something cooled, something blended, something broke. But it does not preserve the exact microscopic path that produced that outline. As time moves forward, the number of lost details grows. The universe becomes more and more smoothed out in terms of information, and this smoothing gives time its direction. The world can move from detailed to blurred, but not from blurred to detailed without deliberate intervention. The idea of forgetting also helps explain why the universe appears to flow from order to disorder. Order is essentially a highly detailed configuration, where information about how the pieces fit together is clear and accessible. Disorder is a state with far fewer constraints. Once information about the precise arrangement of a system has faded, returning it to its previous ordered form becomes a task of unimaginable precision. You would need to gather not only the visible structures, but also the invisible microscopic details that once defined them. Without those details, the system cannot find its way back. A helpful way to visualize this is to imagine a library where every book has been carefully shelved according to topic, author, and date. This neatly arranged library represents a system full of stored information. Now imagine a tremendous gust of wind sweeping through the shelves, scattering the books. The books are still present, but the information about their precise organization is gone. You cannot restore the library to its original arrangement simply by guessing. You would need the exact record of where each book once belonged. Without that record, the library has forgotten its structure. The universe behaves similarly. Once the details are lost, the path back becomes as inaccessible as trying to restore the library from memory after the catalogue has been erased. This cosmic forgetting shapes not only familiar processes like mixing and cooling, but also the evolution of the universe itself. In its earliest moments, the universe was in an incredibly specific state. The distribution of energy and matter had a precise form that allowed everything we see today to unfold. But as time moved forward, gravitational interactions, collisions, expansions, and countless microscopic rearrangements diluted those details. Today, the universe remembers its past only in broad patterns. Galaxies formed, stars ignited, planets cooled. The exact arrangement of each particle in the early cosmos is long gone. That memory has been washed out by billions upon billions of interactions that spread the information beyond recovery. This loss of detail does not make the universe simpler. Instead, it allows complexity to grow in a different way. When information spreads so widely that it becomes irretrievable, the universe gains a kind of flexibility. New structures form, new patterns emerge, and new history unfolds. Forgetting, in this sense, is part of what enables the future to be different from the past. If every microscopic detail remained fixed and recoverable, the universe would behave like a perfectly wound clock, endlessly cycling through rigid patterns. Instead, it evolves with a soft drift, shaped by the interactions that erase old information and make room for new possibilities. The forgetting of microscopic details is what gives time its one-way character. Once the universe loses track of the precise steps that led to a moment, those steps cannot be retraced. The present becomes a blurred version of the past, and the future builds on this softened foundation. Each moment carries less information about what preceded it than the moment before, and in that steady loss, the universe leans forward, from specific to general, from detailed to diffuse, from memory to possibility. In that way, irreversibility is not simply about things changing. It is about the world gradually letting go of the exact paths it once followed. Time moves forward because the past becomes something the universe no longer has the information to recreate. And in that quiet, inevitable forgetting, the direction of cosmic history finds its shape. One of the most surprising ideas in physics is that the world behaves differently depending on the scale you look at. At the smallest levels, nature seems to run by rules that are perfectly reversible. If you were able to track a few particles moving in empty space, you could reverse their motions and watch them retrace their paths exactly. Nothing in the laws that govern their behavior would stop this from happening. Yet when you step back and look at the world you actually live in, reversals never occur. Spilled drinks do not gather themselves. Shattered glass does not reassemble. Heat does not flow back into a warm object once it has escaped. The small-scale rules allow reversibility, yet the large-scale world is full of processes that go only forward. This contrast between microscopic reversibility and macroscopic irreversibility lies at the heart of the arrow of time. To understand the small-scale picture, imagine a single particle drifting through space. It moves according to simple rules. If you change its speed or direction, it responds in a predictable way. If you reverse the particle's motion completely, it will follow its previous trajectory backward. 2 particles behave the same way, so do 3. If you could reverse every detail perfectly, the motion would simply unwind. At this level, nature behaves like a film that could be played backward or forward with no obvious difference. Many of the deepest equations in physics are time-symmetric. They do not care whether time moves forward or backward. But when you zoom out from these tiny particles to something made of enormous numbers of them, the picture changes dramatically. A glass of water contains more particles than you could ever imagine individually tracking. They collide, swirl, bounce, and vibrate in ways that are incredibly sensitive to small changes. If you were to reverse the motion of every particle in that glass at the exact same instant, it would return to its earlier state, but achieving that reversal requires an impossible level of precision. You would need to know the exact position and exact speed of every molecule, right down to the smallest detail, and you would need to reverse them all perfectly at the same moment. If even one particle is slightly off, the reversal fails. This sensitivity is why macroscopic reversals never happen naturally. The particles inside everyday objects interact constantly with their surroundings. A warm drink in a room is constantly exchanging energy with the air, the table, the cup, and even your hands. All of these interactions smear out the precise information you would need to reverse the system. Once the details spread, the door to perfect reversal closes. The system continues forward, not because it cannot run backward, but because running backward requires information that has already been lost. Consider stirring cream into coffee. At the microscopic level, every swirl, eddy, and ripple comes from particles pushing and pulling on each other. If you had a magical way to track those particles exactly, you could in principle reverse their motion and watch the cream gather itself back into a neat white pool. But the number of particles involved is so huge that the exact configuration becomes impossible to track. The number of ways the particles can arrange themselves once mixed is astronomically larger than the number of ways they can exist in a perfectly separated state. Reversing the mixture is technically possible, but the probability of the particles spontaneously coordinating themselves back into that tidy arrangement is so small that it will never happen in the lifetime of the universe. This is where scale transforms what is allowed into what is effectively impossible. At the microscopic level, you can think of particles as tiny actors that follow reversible scripts. But when trillions upon trillions of those actors interact at once, the number of possible outcomes explodes. The direction that is easiest to reach is the one that becomes the real direction of time. It is not that the universe forbids reversal, it is that the universe overwhelmingly favours the path with the most accessible outcomes. The forward direction offers countless ways for particles to arrange themselves. The backward direction offers only a few precise paths, many of which require an unreal level of coordination. You can picture this with a simple analogy. Imagine dropping a handful of confetti into a gentle breeze. Once the pieces scatter, the exact configuration of their positions and motions becomes hopelessly complex. The breeze, the angle of your hand, the shape of each piece, and countless other tiny influences determine how the confetti moves. If you record the moment of scattering, You can always watch the recording in reverse and see the confetti reassemble in your hand. But nothing like that happens on its own in the real world. The real confetti will not suddenly gather itself back and leap into your palm. The backwards motion is allowed by the rules, yet it does not occur because the details needed to make it happen have been lost. This same logic appears in all irreversible processes: heat flowing outward, colours blending, gases spreading, objects breaking, scents dispersing. All of these rely on millions or billions or trillions of tiny interactions. Each interaction is reversible in theory, but their combined behaviour becomes irreversible in practice. Once the details vanish into the complexity of the system, there is no path back to the exact starting point. The system has too many pieces, too many possible patterns, too many ways of drifting into a wider space of outcomes. It is similar to trying to return a shuffled deck of cards to perfect order by tossing it in the air and catching it again. The laws of physics do not forbid the cards from landing in neat numerical order, but the number of possible jumbled arrangements is astronomically larger. The chance that the toss produces the original pattern is so close to zero that, for all practical purposes, it never happens. The world behaves in the same way. It does not forbid neat arrangements. It just rarely stumbles into them once they have dissolved. Macroscopic irreversibility is therefore not a contradiction of microscopic reversibility. It is a consequence of how complexity behaves when many reversible parts interact. The microscopic world is full of detail, exact positions, exact speeds, exact energies. But the macroscopic world does not keep track of these details. They disperse, blend, and fade. Once they're gone, the system loses the ability to trace its way backward. This is why you see events unfolding only forward. It is why heat cools, why mixtures blend, and why processes that begin from special, low-complexity states drift toward more ordinary, high-complexity ones. This difference between what is possible and what is probable defines much of your daily experience. You never expect your coffee to unmix because you instinctively understand how unlikely it is. You trust that a broken object will not repair itself because you know how many things would have to go exactly right. You rely on heat moving outward, not inward. These expectations are grounded not in rigid rules, but in the extraordinary imbalance between the number of ways things can be spread out and the number of ways they can be arranged neatly. The paradox of microscopic reversibility and macroscopic irreversibility is ultimately a story about scale. The small-scale world is full of perfect symmetry and reversible motion. The large-scale world leans heavily towards spreading, smoothing, and drifting forward. One world allows reversals, the other never sees them. And from the tension between these two views emerges the direction of time, the unfolding of events, and the gentle truth that the universe, on its largest stages, always prefers to move ahead rather than retrace its steps. When people first hear that irreversibility comes from probability rather than strict laws, the idea can sound almost too gentle to explain something as universal as the arrow of time. Yet this is exactly what gives the universe its steady forward drift. Nothing in the core rules of physics prevents heat from flowing into a warm object, or cream from unmixing itself, or broken pieces of glass from snapping back together. The laws themselves do not forbid reversals. Instead, the universe leans toward the outcomes that are easiest to reach, and those outcomes outnumber the neatly ordered ones by amounts that are almost impossible to comprehend. Irreversibility does not come from a ban. It comes from overwhelming likelihood. To appreciate this, Imagine a box filled with a huge number of gas particles. At the microscopic level, they bounce around randomly, colliding in ways that are unpredictable but governed by simple rules. If all of these particles start in one small corner of the box, that arrangement is special. It is specific, tidy, and highly organized. There are not many ways for all the particles to cluster like that, but as soon as they begin to move, they drift apart. With each collision, the number of possible arrangements grows dramatically, and because there are far more arrangements where the gas is spread evenly throughout the box, the system almost always evolves toward that state. It is not that the gas refuses to gather again. It is simply that the chance of every particle choosing exactly the right movements to return to the corner is so tiny that it may as well be zero. This tendency toward more possible arrangements is at the heart of entropy. When a system has few available patterns, it is fragile. It sits on a narrow ledge. When it has many available patterns, it is stable. It occupies a broad plateau. The universe moves from the narrow ledge to the broad plateau because the plateau offers countless more ways for things to be arranged. A neatly stacked arrangement of playing cards has just one very special ordering. A shuffled deck has an almost unimaginable number of possibilities. This is why you can shuffle a deck for the rest of your life and never see it return to perfect order. The rules of shuffling do not forbid it, but the odds are so small that you will never live long enough to witness it. Natural processes behave the same way. When you stir a liquid, you are nudging the system away from a very precise arrangement toward an enormous sea of mixed possibilities. Once everything blends, the number of microscopic patterns available becomes enormous. The system could be in any one of them. You would never expect the liquid to separate again because you instinctively sense how unlikely it is that all the particles would coordinate perfectly to recreate the original neat pattern. Even without doing the maths, your experience tells you that the return path is too narrow, too fragile, too specific to be reached naturally. This quiet mathematical imbalance between what is possible and what is probable gives rise to the feeling of direction in time. There are many ways for a warm room and a cool object to exchange energy until they reach a shared temperature. There are almost no ways for that same system to spontaneously become differentiated again without external help. There are countless ways for colours to mix and swirl until they become uniform, but only one way for them to neatly separate back into their starting configuration. The laws governing each particle allow both possibilities. One possibility simply outnumbers the other so overwhelmingly that the outcome becomes inevitable. You can picture this contrast with a simple analogy. Imagine you drop a bag of tiny beads onto a flat table. They scatter in all directions, spreading widely. Now imagine trying to get them to return to their original arrangement by shaking the table randomly. It is not that the beads cannot land in the original pattern. There is nothing physically impossible about that arrangement, but the number of other patterns they can form is so large that the chance of them falling back into the one specific layout you started with is essentially non-existent. The universe behaves the same way. It explores its possibilities at every moment, and the mixed, spread out, balanced states dominate the landscape. This profoundly lopsided balance is what creates time's arrow. It is not that the universe pushes things forward. It is that the forward direction corresponds to a vastly larger set of possibilities than the backward direction. When a warm and cold region swap energy, the forward process has trillions upon trillions of ways to unfold. The reverse process, where exactly the same energy patterns reform, has only a microscopic handful of ways to occur. The math leans so strongly in one direction that time appears to have a built-in flow, but that flow comes from probability, not from any kind of imposed force. One of the most soothing parts of this idea is that it explains irreversibility without requiring anything dramatic or mysterious. You do not need new rules or special exceptions. Tiny particles simply follow their basic motions, and as systems become larger, the combinatorial explosion of possible arrangements makes some outcomes effectively unreachable. The universe drifts into states with more possibilities, not because it prefers them, but because those states dominate the landscape. It is like walking downhill. You can climb back up, but the path downward is easier, wider, and available from almost every step. This perspective softens the way you see everyday processes. When a pot of hot soup cools on the counter, you know it will not suddenly reheat itself. When cream swirls into coffee, you know it will not form a tidy layer again. When a puzzle falls apart, you know it will not reassemble itself spontaneously. None of this is forbidden, yet none of it happens. The improbability is simply too great. Understanding this can make these everyday moments feel less like failures of nature to behave neatly, and more like natural expressions of mathematics at work. It also explains why some things require effort to reverse. Cleaning a messy room takes time and intention, because you are steering the system back toward a highly specific configuration, fighting against the enormous number of ways the room can be disordered. You're not battling chaos, you're battling probability. The messy state is simply more likely. The organized state requires many conditions to be just right. This is why tidying feels like a one-way task. The slightest disturbance can increase the number of possible arrangements dramatically, while keeping things ordered requires continuous attention. This same imbalance appears at cosmic scales. The early universe was in a remarkably special state with low entropy, a state with far fewer possible arrangements than the universe has today. As cosmic history unfolded, the number of possible patterns exploded. Stars formed, planets cooled, galaxies spread. The universe expanded into an ever-growing range of configurations. And because there are so many more paths leading forward than backward, the overall flow of time became a story of increasing probability. Things moved toward the states that were easiest for billions of particles to reach. In a way, the quiet mathematics of improbability acts as a gentle guide. It does not demand, restrict, or command. It simply whispers that some outcomes are overwhelmingly more common than others. This whisper is enough to create the directionality you see everywhere, from cooling drinks to swirling clouds to the unfolding of cosmic history. Irreversibility emerges naturally when the number of available outcomes leans so heavily in one direction that the reverse path becomes invisible. When you understand irreversibility this way, it loses its harshness. It stops feeling like a cosmic rule and starts feeling like a soft unfolding. Processes follow the widest paths. Patterns dissolve into the forms that have the most possibilities. Systems drift into the states that require the least coordination. And in that drift, the world gains its sense of before and after, shaped not by strict laws, but by the gentle mathematics of what is most likely to occur. Life is full of processes that quietly move in one direction. Cells divide and specialize. Energy flows in, is used, and flows back out in different forms. Tissues grow, repair themselves, and eventually wear down. Even the most basic activities of living organisms follow patterns that cannot simply be reversed. You cannot unbreathe a breath, undigest a meal or ungrow a cell. Biology is built on chemistry, and chemistry is built on the movement of energy. Once that energy shifts form, the earlier state becomes something the system cannot naturally return to. Life's chemistry, from the smallest reactions inside a cell to the long arc of aging, is shaped by irreversibility. At the heart of this irreversibility is metabolism. Every living organism, from a bacterium drifting through water to a towering tree drawing sunlight into its leaves, relies on a steady stream of energy. This energy comes in concentrated forms, like sugars, fats, or sunlight. Inside the organism, those concentrated sources are broken down into simpler components. In doing so, they release energy that the organism uses to build, repair, move, and grow. Once this energy has been extracted, it is no longer in the same concentrated form. It disperses as heat or becomes part of molecular waste products. The system does not contain the information needed to rebuild the original molecules perfectly. The process runs forward because the energy transformations required to run it backward are far too unlikely to happen spontaneously. You can picture this with a simple meal. When you eat food, your digestive system breaks it down into tiny pieces. Those pieces release energy that fuels your body. Once the energy is used, it spreads throughout your cells, eventually leaving your body as heat. The nutrients are converted into new materials, waste products, and fuel molecules. Every step of that process involves chemical reactions that move in a particular direction. To reverse it, you would need every molecule to retrace its path, recombining into the exact ingredients you ate. The probability of this occurring is effectively zero. You could wait longer than the lifetime of the universe and never see your lunch reassemble itself. Even inside cells, irreversibility guides nearly every reaction. Many of the biochemical pathways that keep you alive depend on energy gradients, differences in concentration, charge, or structure that give the reactions a direction to follow. A gradient is like a slope. Molecules slide from high energy states to lower ones. Once they reach those lower states, climbing back up the slope requires external work. Cells can force some reactions to run backward, but only with special machinery and a fresh supply of energy. Left alone, these reactions all drift in one direction. This is why living organisms need constant energy input. Without it, the chemistry stops. The system cannot maintain its organization or keep its processes cycling. This need for energy is often explained by saying that life builds order locally while increasing disorder globally. A cell is an incredibly organized structure. It contains membranes, enzymes, genetic material, signaling molecules, and transport systems. All of these pieces are arranged in specific patterns to keep the organism functioning. But building and maintaining that order requires energy. Every time a protein folds into its shape, or a strand of DNA is copied, or a membrane pumps ions across itself, the cell uses energy to reduce its own internal disorder. That energy then disperses into the environment as heat or chemical byproducts, increasing the disorder outside the cell. The cell maintains its structure not by cancelling entropy, but by exporting it. This creates a one-way flow of energy and organization. The idea that living organisms export disorder might sound dramatic, but it is simply a reflection of how energy moves. A tree capturing sunlight uses that energy to build sugars and grow new branches. The sunlight has been transformed into chemical energy stored in wood, leaves, and fruit. But that stored energy will eventually return to the environment, whether through consumption, decay, or fire. The process cannot simply unwind. The photons from the sun will not magically leap back out of the tree and return to their source. The system has forgotten the details of how the energy came in, and so the path back no longer exists. Aging is another expression of irreversibility in living systems. Over time, small changes accumulate inside cells and tissues. Some changes come from chemical reactions that produce byproducts. Others come from environmental influences or simply from the passage of time. These subtle shifts are not perfectly repairable. Even with remarkable biological machinery designed to fix damage, the repairs themselves are irreversible steps. Eventually, the structures within an organism become less flexible and less able to maintain their original organization. Aging is the long, slow record of irreversible processes unfolding across decades. Cells work tirelessly to undo some of these changes, but they cannot reverse all of them. The information needed to return to a younger state gradually fades. Even reproduction, which seems like the most powerful renewal process of all, does not run backward. Each generation carries forward the information it needs to continue life, but it also introduces new variations. These variations cannot be unwound. Once a new genetic combination appears, the previous exact combination is no longer accessible. The chain of ancestry moves in one direction, accumulating diversity as it goes. The process does not cycle, it unfolds. If you look closely at the chemistry of life, you find that every step is shaped by energy transformations that prefer one direction. When a molecule binds to an enzyme, the release of energy makes the reaction efficient. When a cell divides, the processes that copy DNA, split the cytoplasm, and form new membranes depend on energy inputs that cannot be perfectly reversed. Even something as simple as breathing has this quality. You take in oxygen, which your cells use to extract energy from nutrients. As they do, they release carbon dioxide, heat, and byproducts. Once released, those components diffuse away. The breath cannot be undone because the details of the molecule's original states no longer exist. This one-way chemistry gives living organisms their dynamism. Life is a constant flow, not a static sculpture. Cells are always replacing old components with new ones. Tissues are constantly renewing themselves. Even bones, which seem solid and permanent, are always being broken down and rebuilt at a microscopic level. This rebuilding maintains the structure, but it also moves forward. The new version is never exactly the same as the old. Each step in the process comes with tiny irreversible shifts that accumulate gradually. Despite how irreversible life's chemistry is, the overall pattern is beautifully balanced. Living systems use energy to create pockets of order, cells, tissues, organs, organisms, that remain stable for long periods. These pockets are like small islands in a sea of spreading energy. They exist because the organism constantly pulls in concentrated energy and releases it back out in diffused forms, maintaining its structure in the process. The flow gives life its direction. Without it, the organization would vanish. With it, the organism continues to grow, adapt, repair, and eventually change in ways that reflect the passage of time. Seeing irreversibility in biological systems does not make life seem mechanical or rigid. Instead, it reveals how delicately life is balanced between order and flow. You're made of countless processes that depend on tiny, irreversible steps. The firing of neurons, the turnover of proteins, the expression of genes, the release and absorption of energy. Each of these steps plays a part in your internal sense of time. Your body remembers what has happened chemically, but it cannot reverse what has been done. The arrow of time that shapes the universe also shapes you. In this way, Life's chemistry is a gentle reminder that living is a one-way journey, not in a dramatic sense, but in an intimate, continuous unfolding. Every breath, every heartbeat, every spark of energy in your cells is a tiny irreversible step forward, and together, those steps form the quiet, steady rhythm that carries you through your own experience of time. Memory gives time its personal direction. You feel the flow of moments not just because the physical world changes around you, but because your mind holds on to some of those changes and lets others fade. You remember waking up this morning, but you cannot remember tomorrow morning. You recall conversations you've already had, but not the ones you will have in a week. This asymmetry is so natural that you rarely even question it. Yet it is one of the clearest signs that for conscious beings, time has a built-in direction. Your memories face backward, your expectations face forward, and the difference between the two forms the psychological arrow of time. At its simplest, a memory is the brain changing itself in response to experience. When something happens, a sound, a sight, a scent, a thought, a feeling, the brain adjusts the strength of connections between neurons. Some pathways become easier to activate, others become quieter, and new patterns form in the network. These structural changes are physical events. They require energy. Molecules shift, proteins move, chemicals are released. And once those changes take place, the previous configuration is gone. This is why memory formation is irreversible. You cannot unexperience something any more than you can unbreak a glass. You can forget it, but forgetting is not the same as reversing. It is another forward-moving process, shaped by the same chemistry that created the memory in the first place. This is why you store past events but cannot encode future ones. The future has not yet produced the sensory input or chemical signals needed to change your brain. Memory requires a cause, something that happened, something that left an imprint, and causes always precede their effects. The brain cannot adjust its structure in anticipation of details that have not occurred. It can predict possibilities, imagine scenarios, or simulate outcomes, but it cannot store those predictions as memories because the physical changes have no anchor in reality. Predictions are guesses, memories are evidence. In this way, your mind processes information in only one direction. Something happens, your brain reacts, and the reaction alters the landscape of your thoughts in a lasting way. Once the change is made, the brain cannot spontaneously revert to its earlier state. To reverse the formation of a memory, you would need every neuron involved to drop back into its exact previous configuration, rearranging its chemical gradients, protein placements, and electrical properties with perfect precision. The number of cells involved is enormous. The number of molecules is beyond imagining. The odds of such a reversal happening through natural brain activity are essentially zero. As the minutes and hours pass, the fine details of memory begin to soften. Even strong memories gradually lose their sharp edges. This fading is itself an irreversible process. The brain is constantly reorganizing itself, repurposing pathways, strengthening some connections and weakening others. Each adjustment overwrites a small piece of the past. Memories blend, evolve, or distort. They shrink from detailed records into gentler impressions. This is not a failure of the brain. It is part of how a living, flexible system works. To hold on to every detail forever would be overwhelming. The mind must forget in order to function. Forgetting is as essential as remembering, and both processes move forward. This asymmetry gives your experience of time its characteristic feel. You stand on a thin line between what has already happened and what has not. Behind you lies a landscape of memories, some vivid, some faint, some warm, some distant. In front of you lies a space of possibilities, none of which your brain can store until they become real events. The richness of the past and the openness of the future create a natural sense of direction. Even if the physical laws of the universe allowed time to run backward, your consciousness would not follow. You would not suddenly remember tomorrow or forget yesterday. Your mind is built on the flow of information from experience into storage, and that flow runs one way. If you pay attention, you can feel this directionality in the smallest moments. When you hear a sentence, your brain processes each word in order. You do not understand the end of a sentence before its beginning. When you walk through a familiar place, your memories help you navigate by recalling what you've seen before, not what you will see next. When you listen to music, you hear each note as it arrives. You cannot leap ahead to notes that have not yet been played. Every part of conscious experience is anchored by the irreversible nature of memory. Even the feeling of anticipation, waiting for something, wondering about something, hoping for something, arises because the brain knows it cannot store the future. That gap between now and later creates room for expectation. If the brain could encode future events the way it encodes past ones, anticipation would not exist. There would be no sense of moving toward anything. Time would lose its emotional texture. By only allowing memories to form after events occur, the brain creates a clear boundary between what is known and what is unknown. This boundary shapes identity as well. You recognize yourself as the same person from day to day because your brain keeps a record of your history. You remember your childhood, your experiences, your relationships, your successes and mistakes. These memories anchor your sense of self. They also create the understanding that you are older than you were yesterday and younger than you will be tomorrow. You may not think about it consciously, but your identity is stitched together from the irreversible process of storing experience. Without that process, the idea of a personal timeline would vanish. The irreversibility of memory also explains why the past feels solid while the future feels open. The past is recorded in neural patterns shaped by billions of interactions. The future has not yet been carved into the structure of your mind. When you recall something, you're reactivating a pattern that has already been woven. When you imagine something, you are creating a temporary pattern, one that fades unless the imagined scenario eventually becomes real experience. This gives the past a sense of weight, and the future a sense of possibility. There is a gentle comfort in recognizing how the psychological arrow of time mirrors the physical one. Just as heat flows outward, just as scents spread, just as mixed liquids refuse to unmix, the mind, too, follows a path where information moves forward. You cannot reverse the changes your experiences create, but that is what makes life coherent. The past becomes story, the present becomes experience, and the future becomes potential. The one-way flow gives structure to every moment you live, and even though the brain forgets, forgetting is not the opposite of remembering. It is simply another step in the same direction. Old details dissolve, new patterns form, and the landscape of memory shifts as you move through your life. In losing some information, the mind makes space for what comes next. The arrow of time does not only unfold in the world around you, it unfolds inside you, shaping your thoughts, your memories, and your unfolding sense of being carried gently forward. Radiation is one of the quietest and most persistent examples of irreversibility in the universe. Every warm object, Every glowing ember, every light bulb, every star, and even your own body constantly sends energy outward in the form of light or heat. Once that energy leaves, it does not return in any meaningful or coordinated way. It spreads out into the surrounding space, diluting as it goes, drifting into wider and wider regions until it becomes impossible to gather again. This gentle outward flow is one of the strongest anchors of the arrow of time. It ensures that certain changes can never be undone, because the energy required to undo them has already travelled too far to matter. To understand why radiative processes are so one way, imagine standing in a dark room holding a small torch. The moment you switch it on, the light spreads outward. It illuminates the walls, the floor, and anything else in the room. But once the light has bounced around, it does not reorganize itself into a tidy beam that returns to the torch. The photons scatter, reflect, and diffuse into the environment. After bouncing around a few times, they end up as tiny amounts of heat absorbed by surfaces. No matter how long you wait, the room will not funnel all those photons back into the bulb. The energy is left in a distributed form that cannot be gathered again. This basic fact holds for everything that emits radiation. Warm objects glow in the infrared range, constantly losing energy to the surrounding space. You cannot see this glow with your eyes, but you can feel it. Stand near a heated oven, and warmth spreads toward you. If you step away, the oven does not suddenly reclaim that heat from the room. The warmth disperses, mixing with the environment until the entire space shares it. Even if you seal the room perfectly, the energy would bounce around randomly until everything reached the same temperature. None of those random movements would pick out the oven in reverse and return the heat. This is the essence of why radiation is irreversible. Emitted energy spreads in all directions, not just backward. When a warm object radiates heat, the energy travels outward in an expanding sphere. The area that sphere covers grows rapidly. Within moments, the radiated energy occupies a region thousands or millions of times larger than the object that emitted it. Gathering the energy again would require every single tiny piece of it to trace back through every collision, reflection, and scattering event. The chance of that happening spontaneously is so small that the universe effectively never allows it. Stars offer the most dramatic example. A star shines because nuclear reactions in its core generate enormous amounts of energy. That energy travels outward through the star's layers and then radiates into space as light and heat. Once released, that energy continues travelling forever unless it hits something. It spreads across unimaginable distances. A single photon from the sun might wander through space for thousands of years before being absorbed by a dust grain in a remote corner of the galaxy. There is no mechanism by which sunlight can return to the sun. The star can never unshine, because the energy that left has vanished into the vastness of space. Even the smallest radiative losses reveal this one-way behaviour. A hot cup of tea on a table cools partly because it radiates heat into the room. The radiation leaves in all directions as infrared light. Those little packets of energy bounce around, warm the surrounding air slightly, and then disperse further. They will never reunite and reheat the tea. The tea could be heated again, but only with new energy from an external source. The original radiated energy is gone from the perspective of the cup. It still exists somewhere, but it is no longer accessible in a way that can reverse the cooling. This one-way movement of radiation is tied closely to entropy. When energy is concentrated, such as inside a warm object, it is able to do more work. But when that energy radiates outward, it spreads into trillions of different possible arrangements. The spread out state represents far more microscopic patterns than the concentrated one. The universe naturally drifts towards states with more possible configurations because those states are overwhelmingly more probable. Once energy spreads, retightening it into its original form becomes practically impossible. Radiative loss ensures that systems become more uniform, more diffused, and more difficult to reverse. Consider how light behaves when it leaves a candle flame. The flame emits photons in every direction. Those photons travel outward in straight lines unless they encounter a surface. Some scatter, some get absorbed, some escape into open space. After a split second, the original cluster of photons is spread over a huge area. After a single minute, it may be spread over kilometers. There is no guiding mechanism that brings them home. Radiation is like scattering a handful of glitter into the wind. The individual pieces do not disappear, but they become so widely dispersed that gathering them again is essentially impossible. This outward drift of energy also explains why objects eventually cool to their surroundings. Even in a vacuum, where there is no air to carry heat away, an object will still lose energy through radiation. A hot metal rod left in the emptiness of space will cool because it glows invisibly in the infrared, sending its energy outward. The coldness of space is not actively drawing heat away. The rod is simply shining energy outwards, and there is nothing to stop the process. And once that energy is gone, it will not return. The direction is fixed. Radiation also locks in the arrow of time because emitted photons carry information about the past. When light leaves an object, it encodes something about the object's temperature, structure, or movement at that moment. Once emitted, these photons travel away at high speed. They take their information with them. Unless an observer captures that radiation, the universe has effectively lost the details about what produced it. There is no mechanism to reabsorb the photons and reconstruct the original state. This loss of information is a hallmark of irreversibility. It means that the past becomes harder to reconstruct as more radiation escapes into space. You can see this idea in the night sky. When you look at distant stars, you're seeing light that left them many years ago. That light will never return to the star. It has become part of the cosmic background of information. Every star is constantly leaking energy into the universe, marking an arrow of time that points away from its childhood and toward its eventual cooling. Radiation tells the universe which direction is forward because every emitted photon is a tiny declaration that a moment has passed. Even your own body is part of this radiative story. You emit infrared light constantly. This radiation is one of the ways your body regulates its temperature. The energy you radiate does not circle back to warm you again. It disperses into the room. If you stand in a freezing environment, this emission happens faster than usual, which is why you lose heat so quickly. You're constantly shining, even if you cannot see it. And this shining is one of the reasons your body cannot remain warm without continuous energy input. The irreversible nature of radiative processes is one of the universe's simplest truths. It does not rely on deep mathematics or exotic physics. It comes from the straightforward observation that energy spreading outward becomes too dilute to gather again. Whether the source is a cup of tea, a heated floorboard, a candle flame, or a star, the result is the same. Once the energy leaves, it does not return in a coordinated way that could restore the earlier state. And so radiative processes quietly enforce a one-way direction in time. Warmth moves outward, light escapes, energy spreads, information drifts away on photons. These tiny, irreversible steps accumulate across everything that radiates, from the smallest objects to the largest stars. In their quiet, unavoidable way, they anchor the arrow of time, ensuring that the universe continues its steady progression from concentrated energy to dispersed light scattered across the vastness of space. A crack forming in a surface is one of the simplest examples of irreversibility you can witness. A vase slips from your hand, strikes the floor, and fractures into pieces. A plate chips on the edge of a counter. A tiny fracture spreads across a phone screen in an instant. These moments feel sudden and almost effortless, and yet repairing the damage is anything but. Fixing something takes time, patience, and external help. Undoing every detail of the breakage, returning every fragment to its original position, every bond to its previous strength, is practically impossible. The world makes breaking easy and unbreaking difficult because damage increases disorder, and disorder offers far more possibilities than order ever can. When an object is whole, its atoms sit in a carefully arranged structure. Each bond and connection fits into a specific place. This ordered arrangement represents a limited number of possible patterns, but as soon as force is applied, a drop, a strain, a sudden twist, the structure is disrupted. Bonds snap in unpredictable ways. Fragments follow chaotic paths shaped by tiny details like their angle of impact, the roughness of the surface, or the internal stresses already present within the material. Once the object breaks, the number of possible configurations increases dramatically. There are countless ways for the pieces to scatter, and only one precise way for them to be arranged as they were before. This is why breakage increases disorder. A crack frees the material from its rigid arrangement and allows it to move into a much broader landscape of possible outcomes. Once it begins, the fracture spreads because the broken region can no longer carry stress effectively. The stress shifts to the surrounding material, which then fails more easily. This creates a cascade, a chain reaction where the damaged area expands rapidly. In a solid object, a crack tip focuses the stress into a tiny region. That focus allows the crack to grow with very little additional effort. You can think of it like a zipper opening. Once the first tooth is undone, the next ones come apart quickly. The difficulty of reversal lies in the loss of the original structure. When a crack forms, the material around it changes in ways that are not easily undone. Tiny deformations remain even if the pieces are pressed back together. The surfaces that were once perfectly joined no longer fit with microscopic precision. The random scattering of fragments disperses information about exactly how the object used to be arranged. Returning those fragments to their precise original orientation would require a level of detail far beyond what natural processes can achieve. This loss of structure happens even on a much smaller, less dramatic scale. Think about bending a metal paperclip back and forth. The metal weakens and eventually snaps. Each bend reshapes the microscopic structure of the metal, changing how the atoms are arranged. These internal changes accumulate until the metal can no longer withstand the stress. The break is not reversible because the original arrangement of the metal structure has been overwritten. Even before the snap, the internal damage that leads to the break is permanent. Cracks also behave in ways that favor progression over healing. A crack tip concentrates stress, making it far more likely for the crack to grow than to shrink. Healing, by contrast, would require atoms to return to the crack and reconnect in exactly the right arrangement. This coordination is far too specific to happen spontaneously. The crack continues to grow, because there are many ways for the damage to expand, but very few for it to undo itself. Once the crack reaches a critical size, the rest of the material can fail suddenly. This is why objects sometimes seem to break all at once, after a small flaw has been growing quietly for a long time. Even in biological systems where healing is possible, the reversal is not perfect. When a bone fractures, the body repairs it by forming new bone tissue. The healed bone can be strong, but the original structure is not restored atom by atom. Instead, the body creates a new arrangement that compensates for the damage. Scar tissue behaves the same way. It reconnects the wound but does not replicate the original pattern of cells. Healing is not rewinding. It is moving forward with the new structure. Even living organisms cannot reverse the exact microscopic details that were lost. On a larger scale, damage shows how systems prefer to slide into states with more possibilities. A shattered plate can be arranged in hundreds of scattered patterns. A cracked screen can split in any number of branching lines. A dented car panel can warp in a variety of shapes. The original, unbroken state represents only a single configuration among many. Because these broken states offer so many more arrangements, the system drifts toward them when stressed. This drift does not require effort. It happens naturally when forces push the object beyond its limits. The ease of damage also explains why repair is so deliberate. To fix something, you must guide the system back toward a precise arrangement that is no longer natural. You must supply energy, tools, time, and careful attention. Even then, the repair rarely becomes indistinguishable from the original. Microscopic differences always remain. The repaired state is another arrangement in the landscape of possibilities, not a restoration of the original one. This contrast between the ease of breaking and the difficulty of repairing is rooted in probability. There are far more ways for something to be broken than to be whole. There are far more ways for a structure to be damaged than to be flawless. Even the most robust objects have many failure modes but only one perfect form. This imbalance is why damage spreads easily, while healing requires intention. The forward path has many possibilities. The reverse path has only one. If you look at the world with this in mind, you begin to see a soft metaphor emerging. Fragility is not a flaw in the universe. It is a natural expression of how systems behave when stressed. Nothing is immune to the imbalance between order and disorder. A mountain erodes grain by grain. A tree loses branches in the wind. A stone statue slowly wears down under rain and sun. Over time, cracks spread, edges soften, and details disappear. These changes do not violate any rule. They simply follow the slope created by probability. And in a more personal sense, fragility can be a gentle reminder of the flow of time. The objects around you bear marks of their history. A chipped mug tells the story of a moment that cannot be undone. A worn book shows how often it has been read. A scratched surface records the interactions it has endured. These signs of use are natural. They reflect the fact that the world moves forward, not backward. Damage is a physical trace of time's passage. When seen this way, the ease of breaking is not something to fear. It is a quiet demonstration of how the universe leans toward the states that are most abundant. Objects change, structures wear, and cracks spread, because the specific arrangement that kept them intact is only one among countless possibilities. As soon as that arrangement is disturbed, the system explores the wider space available. Repair, when possible, creates a new configuration. It does not reverse the old one. In that sense, every crack and fracture is a reminder of the gentle imbalance that shapes everything. The universe allows reversal in theory, but rarely delivers it in practice. The forward path is broad and easy. The backward path is narrow and precarious, and so things break, drift, scatter and settle into states that reflect the immense number of ways they can be arranged. Damage is simply another expression of irreversibility, a small, tangible sign of the world moving steadily along its natural one-way flow. Geological time moves at a pace so slow and steady that it can feel almost outside human experience. Mountains rise not in years or centuries, but in millions of years. Rivers carve valleys grain by grain. Coastlines shift like breathing, each tide carrying a few more particles away. And deep beneath the surface, layers of sediment quietly accumulate, recording the history of the planet in thin, delicate sheets. These processes unfold over such long stretches of time that they become some of the clearest expressions of irreversibility. Once a mountain has worn down or a sediment layer has formed, the exact past cannot be reclaimed. The Earth moves forward through its own vast timeline, reshaping itself with steps that cannot be unwound. One of the most familiar forms of geological irreversibility is erosion. No matter where you look, Earth's landscapes are constantly being weathered by wind, water, temperature changes and gravity. A raindrop falling onto bare soil dislodges a grain of earth. A river steadily cuts through rock, rounding sharp edges and carrying fragments downstream. Waves grind pebbles into sand and sand into finer grain still. All of these actions slowly wear the land away, but none of them run in reverse. You never see grains of sand spontaneously leap back onto a cliff to rebuild the rock they came from. You do not see river valleys uncarve themselves. You do not see broken fragments of stone assemble into sharp, unweathered peaks. Erosion occurs because energy from the environment, flowing water, wind, sunlight and temperature shifts, pushes material into states with more possible arrangements. A rugged cliff has a very specific structure. Once it begins to crumble, the pieces fall into many possible configurations. They may become rocks, gravel, sand, or sediment. Each step away from the original arrangement opens up millions of new possibilities, and just like with mixing or heat flow, reversing the process becomes so unlikely that it may as well be impossible. The fragments do not remember where they came from. The details of their original positions dissolve with every collision and every journey downhill. Mountain building follows a similar logic. Mountains rise when tectonic plates collide, forcing the crust upward. This process requires enormous amounts of energy from deep within the planet. Once a mountain is created, erosion begins to wear it down immediately. Wind shears off exposed surfaces. Ice creeps into cracks, widening them as it freezes. Streams carry the debris away. Over time, even the tallest peaks shrink into gentle hills, and those hills eventually flatten into plains. The original towering structure is lost. To rebuild it naturally, the same tectonic collision would have to occur again, with the same strength, same timing, and same alignment, a level of precision that is far beyond what the planet's chaotic interior can replicate. Mountains can rise again in similar places, but never in exactly the same form. Over deep time, the material removed from mountains and cliffs eventually settles somewhere else. Rivers slow as they reach flatter ground, dropping sediment grain by grain. Lakes accumulate fine layers of mud. Oceans gather vast blankets of sand, shells, and biological remains. These sediments, once laid down, form some of the most remarkable geological records on Earth. Each layer captures a moment in time, a flood season, a volcanic ash fall, a long summer of growth, or a shift in climate. Over millions of years, these layers build up into thick sequences that act like pages in a history book. What makes sedimentary layering such a strong example of irreversibility is that once these layers form, they cannot naturally return to their previous states. If you drilled into a cliff of layered sandstone, you would reveal sheet after sheet of ancient time, each layer representing a different environment or era. The materials in these layers were once part of mountains, riverbeds, beaches, or soils. But the specific conditions that created them are long gone. The sands do not unlayer themselves. The sediments do not unscramble into their original sources. Instead, they remain locked in place until uplift or erosion exposes them, writing new chapters in their ongoing transformation. Earth's surface behaves this way because destruction, dispersion, and deposition have countless possible outcomes, while reconstruction requires extraordinary precision. A slope can collapse into thousands of rock fragments and settle into any number of stable positions, but to rebuild the slope exactly as it was, angle for angle, grain for grain, is not something nature does on its own. Gravity, water, and wind push landscapes forward through irreversible steps, nudging them from more ordered arrangements to less ordered ones. Time smooths sharp edges and blends distinct patterns, just as it does at microscopic scales. There's a gentle comfort in understanding how these immense processes reflect the same principles that guide smaller ones. Earth's irreversibility feels different only because the timescales are vast. A cliff eroding looks static to the human eye because the changes unfold slowly. A single year may only remove a handful of grains. A single lifetime may see only slight shifts in a coastline. But stretch your perspective across 10,000 years, and rivers carve canyons. Across 1,000,000 years, mountains crumble. Across 100 million years, entire continents drift, merge, and split again. The one-way nature of these changes becomes obvious on the scale of deep time. Stratigraphy, the study of layered rocks, reveals this directionality especially clearly. When geologists examine a sequence of layers, they read the record from bottom to top. The oldest layers lie beneath newer ones because sediment always accumulates on top of what came before. You can never find a natural sequence where younger layers are buried beneath older ones without some dramatic geological process like folding or faulting. The stacking of sediments has a built-in direction. Each layer represents a former surface that is now part of the past. The planet archives time in stone. This layering means that certain conditions can only happen once. A volcanic eruption may leave a thin ash layer across a landscape. Once buried, that layer remains a timestamp. It cannot return to the surface unless erosion removes everything above it. And even then, exposing the ash does not undo the eruption. It simply reveals the evidence. Geological events are recorded but not reversed. Deep time irreversibility also shows up in the movement of continents. The slow drift of tectonic plates pushes oceans open and squeezes them shut. Mountain ranges rise where plates collide and sink when the plates move apart. These changes unfold so slowly that they appear still, but nothing about them runs backward. A continent will not return to a previous position with perfect accuracy. By the time it comes near that region again, millions of years of erosion, sedimentation and uplift will have reshaped it entirely. The past becomes unrecoverable not just because the land has moved, but because the information about its earlier state has dispersed. Geological irreversibility also touches the climate. Ancient climates leave traces in rocks, ice cores and fossils. But once a climate shift occurs, whether a period of global warming, glaciation or volcanic cooling, the exact previous conditions cannot return. The system has changed too much. New sediments have formed, new organisms have evolved, new layers have locked in the record of the transition. The Earth does not cycle back to past climates with perfect precision. It evolves forward, carrying the marks of its earlier states but never resetting them. These ideas might seem vast or abstract, but they reflect the same simple principle you see in everyday irreversibility. Once a system's details disperse into countless possibilities, the exact original state cannot be recovered. A broken rock, a carved canyon, a layered sediment, all of these represent information that has been spread out and transformed. The Earth forgets its earlier forms just as a cooling drink forgets its earlier heat, or a stirred mixture forgets its separated colours. Yet within that forgetting is something peaceful. The landscapes around you, hills, mountains, plains, cliffs, are the result of slow, one-way processes that have been unfolding for millions of years. They remind you that time flows forward for everything, not just for living beings. The world around you has its own memory written in stone, and its own direction shaped by irreversibility. And when you look at a weathered rock or a layered cliff face, you are seeing a gentle record of that forward journey. A quiet archive of the planet's slow but unstoppable flow through deep time. The expansion of the universe is one of the grandest examples of irreversibility. It acts on a scale so vast that it becomes almost impossible to sense directly, yet it shapes every moment of cosmic history. Galaxies drift farther apart. The fabric of space stretches. Light travelling across the universe is pulled into longer, redder wavelengths, and as the expansion continues, the universe becomes cooler, more diffuse, and more spread out. Unlike many things in nature, this expansion shows no sign of running backward. There is no hint that the cosmos will suddenly shrink or unwind itself. Instead, the universe moves steadily outward, marking an arrow of time that reaches from the earliest instants to the far future. To understand why expansion creates a deep direction to time, imagine galaxies suspended in a stretching piece of fabric. Each galaxy sits in place while the fabric beneath it expands. As the fabric grows, the distances between galaxies grow with it. The galaxies are not flying apart through space. Space itself is enlarging. This stretching changes everything. Light must travel across increasing distances. Patterns of matter become more spread out. Energy disperses into ever larger volumes. These changes cannot run in reverse naturally because they involve countless tiny details that the universe would need to coordinate perfectly to collapse again. The expansion does not forget. It only moves outward. This outward motion began with the Big Bang. Not an explosion in space, but the rapid expansion of space itself. That expansion set the stage for everything that followed. The formation of matter, the cooling of the cosmos, the birth of stars, the growth of galaxies, and the slow emergence of structure. When the universe was young, it was hot and dense. As it expanded, it thinned and cooled. These early conditions were incredibly specific, like a precise arrangement of ingredients. As the expansion continued, the universe explored an enormous range of new possibilities. Dense regions stretched, energetic patterns dispersed, radiation spread out and softened. To reverse this process, every particle, photon, and fluctuation would have to retrace its steps with unimaginable precision. The chance of this happening through natural processes is essentially zero. Cosmic expansion also ties directly into thermodynamic drift. As space grows, the energy within it becomes less concentrated. Photons become weaker as their wavelengths stretch. Matter spreads out, lowering its temperature. The universe moves from a state with fewer possible arrangements, the compact, hot early universe, to one with vastly more possibilities. This shift mirrors the same principle seen in mixing, cooling, and dispersal on smaller scales. Systems tend to move towards states with more possible microscopic patterns. In the universe as a whole, expansion is the mechanism that enables this drift. It increases the volume of space, creating room for energy to spread out in ways that are irreversible. One of the clearest signs of this directionality is the cosmic microwave background, the faint afterglow of the early universe. This radiation once filled the cosmos as blazing light, but expansion has stretched its wavelengths over billions of years. Today it is a gentle, uniform bath of microwaves that permeates all of space. It carries information about a time long past, and that information has been thinned, softened, and cooled by the expansion. This is a permanent change. The radiation will never regain its earlier intensity. The universe cannot compress itself back into the hot, dense state that existed shortly after the Big Bang. The details of that early moment have been smoothed away. You can also see the arrow of time in how galaxies form. In the early universe, matter was nearly evenly distributed. Small fluctuations in density grew slowly as gravity pulled matter together. Over billions of years, these fluctuations became galaxies and clusters of galaxies. This structure did not appear instantly. It formed in response to the expansion and cooling of the universe. If the cosmos were somehow rewound, the galaxies would not simply fold back into the smooth, balanced early state. The reversal would require undoing every gravitational interaction, every collision, and every drift of matter, a level of coordination the universe does not support. The expansion transformed the early universe into something far more structured, and that transformation cannot naturally run backward. As expansion accelerates, a discovery made in the late 1990s, the arrow becomes even more pronounced. The universe is not just growing, it is growing faster with time. This acceleration appears to be driven by dark energy, a mysterious component of the cosmos that creates a kind of stretching pressure. As space grows more quickly, galaxies move farther apart at increasing speeds. Light from them becomes more stretched. Over extraordinarily long time scales, the night sky will change. Distant galaxies will slip beyond the range of visibility as the expansion pulls them away faster than their light can reach us. This is not something that can be undone. Once a galaxy's light falls behind the expansion, it is lost from view forever. The expansion also affects how stars evolve. As the universe grows older and more diffuse, star formation slows down. There are fewer dense clouds of gas left to form new stars. Existing stars will burn through their fuel and fade. When the last stars eventually dim, the universe will enter a long, quiet stage dominated by cold remnants and faint radiation. This future is filled with irreversible steps. Stars cannot unburn their fuel. Light cannot untravel the distances it has crossed. Matter cannot reconcentrate itself without external input. The expansion ensures that everything moves toward a cooler, smoother, more diffuse state. There is something gentle about this outward drift. It is not violent or abrupt. It is a slow, steady stretching that shapes cosmic history in a way that feels peaceful when viewed from a human perspective. The same principle that guides the spreading of heat or the mixing of colours on Earth also guides the evolution of the universe. Systems move from concentrated states to diffused ones because there are far more ways to be spread out than tightly packed. On the grandest scale, expansion is the mechanism that gives space itself the room to follow this tendency. The idea that the universe grows instead of contracting may seem asymmetric, but it reflects the initial conditions. The early universe was incredibly ordered in a physical sense. It was smooth, uniform, and hot, a rare combination among all possible configurations. As soon as expansion began, the universe drifted into a vastly larger set of possibilities. Once those possibilities were explored, there was no natural path back to the original state. Expansion is not simply a movement outward. It is the universe settling into its most probable states. When you look into the night sky, you are seeing this one-way journey. The light from distant galaxies reveals the expansion in action. The red shift of starlight shows how space has stretched since the moment the light was first emitted. This stretching continues every second of every day, even though you cannot feel it. It is the quiet heartbeat of cosmic time. And in the vastness of this slow outward motion, there is a sense of calm. The universe is not rushing toward a dramatic end. It is drifting, cooling, and unfolding. Every galaxy, every star, every cloud of gas participates in this gentle expansion. It is a direction that cannot be reversed, a deep arrow woven into the fabric of reality. Through it, the cosmos records the passage of time in the grandest way possible, by continuing to grow. Black holes are often described as cosmic one-way doors, and in many ways that image captures their essence perfectly. They are regions of space where gravity becomes so strong that nothing, not light, not matter, not even the fastest moving particle in existence, can escape once it crosses a boundary called the event horizon. This boundary is not a physical surface, but rather a threshold in the structure of space-time. Before crossing it, escape is possible if you have enough speed or energy. After crossing it, escape is no longer an option. The event horizon marks a literal point of no return, making irreversibility not just likely, but unavoidable. To grasp the meaning of no turning back, imagine approaching a waterfall in a canoe. Far upstream you can paddle in any direction. As you drift closer, the current grows stronger, making it harder to turn around. At some point you reach a line where the pull of the water becomes stronger than any paddling effort you could muster. That line is your personal event horizon. Once you cross it, the journey downward cannot be reversed. Black holes behave in a similar way, but the river is space-time itself. The inward pull is not water, but gravity so intense that even light cannot climb out. What makes this so deeply irreversible is the way information behaves once it falls into a black hole. In everyday life, information is tied to the arrangement of matter and energy. If you drop a book, its information does not vanish. You can pick it up and still read it. If you blend two liquids, the colors mix, but the molecules still contain all the underlying details. In principle, enough knowledge could reconstruct the earlier state. But black holes complicate this comfortable view. Once something crosses the event horizon, the details of what it was become sealed away. From the outside, all that remains visible is the black hole's mass, its electric charge, and its spin. Everything else, the structure, the complexity, the information, disappears behind the horizon in a way that cannot be accessed again. This disappearance of accessible information is what makes black holes so tightly connected to entropy. Entropy measures the number of possible arrangements a system can have. A higher entropy corresponds to more possible microscopic patterns. Surprisingly, black holes have the highest entropy of all known objects. A black hole with a given size has far more possible internal states than any star, planet, or galaxy of comparable mass. This means that when something falls in, a star, a planet, a cloud of gas, the total entropy of the black hole increases. And because entropy naturally rises over time, black holes represent a kind of endpoint in this tendency. They gather information, absorb complexity, and convert it into something inaccessible. Their very existence reinforces the direction of time. Part of this irreversibility comes from the way space-time itself is shaped around a black hole. The event horizon prevents any signal from inside from reaching the outside universe. Nothing about the internal structure can be transmitted back. This barrier means that the black hole cannot simply release what it has taken in, at least not in any familiar form. Some theories suggest that information may eventually emerge through subtle quantum processes such as Hawking radiation. But even if this is true, the information would not return as the detailed structure that went in. It would seep out as faint radiation spread across enormous spans of time. The essence of what fell in would be transformed beyond recognition. In practical terms, this makes black holes some of the most irreversible objects in existence. Their growth is a one-way process. Their influence on the surrounding universe is felt through gravity and radiation, but not through return or recovery. Once the event horizon expands to include new matter, that matter is part of the black hole's future forever. No natural process will take it back out in the form it once had. The star that fell in will not reappear. The gas cloud will not drift back out. Even the light that tried to escape at the last moment will find itself bent inward and lost. Despite how dramatic this seems, there is something calming about the idea when viewed from a gentle perspective. Black holes are not cosmic monsters. They're simply extreme expressions of the same rules that shape everything else. They follow gravity, thermodynamics, and quantum physics. They obey the same principles that cause heat to spread, cracks to form, and galaxies to drift apart. The difference lies in scale and intensity. Where a cooling drink radiates heat into a room, a black hole radiates information into the universe's deep future through faint, nearly eternal processes. Where water swirling in a glass erases patterns quickly, a black hole erases them in ways that span unimaginable spans of time. And even though black holes represent the ultimate point of no return, their existence helps tie together the story of the universe's irreversibility. They take the tendency towards spreading, cooling, and smoothing to an extreme, concentrating mass while hiding the details of what created them. Yet they also slowly leak energy through Hawking radiation, ensuring that even they are not completely eternal. Over extraordinary timescales, a black hole will evaporate, releasing its mass back into the universe as faint heat. But this too is an irreversible process. The black hole does not restore what it swallowed. It dissolves slowly, leaving behind a warm whisper in the darkness. If you picture a black hole not as a destructive force but as a quiet cosmic sink, a place where the universe's complexity is gently folded away, the idea becomes less frightening and more serene. The event horizon is not a violent edge. It is simply a boundary beyond which the universe cannot communicate back. The information that crosses it becomes part of a deeper story, one written in gravity rather than light. And so black holes, though dramatic in reputation, offer a calm lesson about irreversibility. They show that some boundaries cannot be uncrossed. They reveal how information can move in one direction and not the other. They embody the rise of entropy in a form so profound that even space-time bows to it. In the heart of a black hole, the arrow of time is not just suggested, it is carved into the fabric of reality. Seen this way, black holes are simply the universe's quiet way of saying that not everything can be undone, and that some journeys only ever go forward. Across the universe, every warm object slowly cools, stars release their brilliance into the darkness, planets radiate their hidden heat into space, moons, asteroids, and frozen worlds all glow faintly in the infrared, giving away whatever warmth they still hold. And once that heat is released, it cannot be reclaimed. The energy drifts outward forever, thinning as it goes, until it is effectively lost to the vastness of space. This long, slow cooling of celestial bodies is one of the gentlest examples of irreversibility on the cosmic stage. It gives the universe a sense of aging, a quiet unfolding in which worlds grow colder and stars burn through their limited stores of fuel. Consider a planet like Earth. Beneath the crust lies a reservoir of heat left over from its formation billions of years ago. When the planet first condensed from dust and gas, countless collisions and gravitational contractions filled its interior with intense thermal energy. Over time, that heat has been escaping steadily. Molten rock circulates through the mantle. Volcanoes release some of the planet's internal energy, and the surface radiates warmth out into space every moment of every day. This radiated heat travels outward at the speed of light. It does not reverse direction or fall back into the planet. Once it leaves, it becomes part of the cosmic background of thermal energy. The interior of the world grows cooler with time because the heat that sustained its early fierceness cannot return. Even planets that seem cold and quiet today, like Mars or Mercury, once held far more energy. Mars likely had warm oceans and a thicker atmosphere in its early history. Mercury may have possessed a more active and dynamic crust, but as these worlds radiated their heat into space, they fell into quieter states. Cooling transformed their surfaces, altered their climates, and slowed their internal motions. The energy they lost through radiation scattered into space in patterns far too complex to reverse. Those ancient heat signatures drifted outward and are now spread across regions so vast that gathering them again would require undoing billions of years of cosmic expansion. Moons cool as well. A moon like our own was once covered in oceans of molten rock. Over billions of years, that molten surface solidified as the heat escaped. The moon still radiates energy, but only at a very faint level. Inside, it is largely frozen. The heat that once made it glow has long since spread into the cold of space. No natural process can return it. The moon's cooling is complete in the sense that the past cannot be restored. There is no path back to its fiery youth because the details of that earlier state have been lost in the vast dispersal of radiated energy. Asteroids and comets, though small, follow the same pattern. When they formed, they absorbed energy from collisions and radioactive elements. Today they radiate gently into space, losing whatever warmth they once held. Their cooling is irreversible because the heat they emit does not gather into neat patterns that could restore them. It spreads outward in all directions, becoming too diluted to reclaim. The same principles that keep a warm cup from reheating itself apply, but on scales of millions of kilometers. The difference is only in size and time. Stars represent the most dramatic form of cosmic cooling. A star shines because nuclear fusion in its core turns mass into energy. That energy flows outward and radiates into the darkness. Every photon that escapes is one more piece of the star's internal energy that will never return. Over billions of years, a star steadily empties its reservoir of fuel. Once the fuel is gone, the star changes form. Depending on its mass, it may expand into a red giant, shed its outer layers, collapse into a white dwarf, or explode as a supernova. But in every case, the cooling process continues. White dwarfs fade slowly as they radiate their leftover heat. Neutron stars cool at extraordinary rates before settling into faint cold darkness. Even black holes, though extreme in nature, radiate energy across incomprehensible timescales. This radiative cooling defines cosmic time. Young stars burn hot and bright, shaping the early development of galaxies. Middle-aged stars like the Sun radiate steadily, nurturing planetary systems. Older stars fade, and their remnants cool into stillness. When astronomers measure the heat of distant worlds or the temperature of stellar remnants, they are reading a clock written in thermal energy. The cooler the object, the older it tends to be. Heat becomes a kind of memory, not one that can be replayed, but one that slowly fades as the object ages. The reason this cooling is irreversible lies in the nature of radiation itself. When a warm surface emits light or heat, that energy spreads outward into space. It fills larger and larger volumes, thinning with distance. There are countless ways for that energy to disperse, but only one way for it to return. Every photon would have to retrace its exact path. This is so improbable that the universe effectively does not allow it. The heat that leaves a star does not reverse course. The warm glow that leaves a planet does not gather itself again. The cooling is permanent because the radiated energy dissolves into an ever-expanding environment. Cosmic aging is therefore peaceful, slow, and guided by this unidirectional flow of energy. Worlds and stars begin their lives hot and intense. They radiate away their heat, and they drift toward quieter, cooler states that reflect the passage of time. Nothing about this process is rushed. The cooling of a planet or star takes billions or trillions of years. It is a kind of thermal settling, a gradual release of energy that lets celestial bodies move toward equilibrium. Even in this cooling, there is beauty. A glowing star is a reminder that energy is flowing outward from a place where it is concentrated to the vastness where it can spread. The warmth Earth emits each night is a sign that the planet is slowly returning its ancient heat to space. The very faint glow of a distant brown dwarf or a fading white dwarf is the last light of a long cosmic journey. And far into the future, long after most stars have faded and planets have cooled to quiet darkness, this irreversible process will continue. The universe will grow colder and more diffuse. Energy will spread thinner and thinner across space. This cooling will not stop because the energy that leaves celestial bodies cannot reverse its course. Time's direction becomes tied to this long dispersal. Seen in this way, cosmic cooling is a serene reminder that everything in the universe follows the same one-way flow. Whether it is a melting glacier, a cooling cup of tea, or a fading star, the warm energy moves outward, never inward. The cosmos drifts gently from heat to cold, from brilliance to stillness, carrying every world and every star along its quiet, irreversible path. Information feels like something weightless and abstract. A string of numbers, a sentence in a book, a file stored on a computer. It seems as though it can appear, disappear, and rearrange itself freely without any physical consequences. But at its core, information is tied to the physical world. It is stored in atoms, magnets, electrical charges, and patterns of energy. And because of this, information obeys the same rules that govern everything else. One of those rules is irreversibility. Whenever information is erased, the universe must pay a price. Something becomes more disordered. Energy spreads. Details are lost. Information loss is inherently a one-way step, and in that sense it mirrors the wider arrow of time. To see why deleting information increases disorder, think about how a computer stores data. At the most basic level, information in a digital device is represented using tiny physical states. A memory cell might hold a small amount of electric charge, or a magnetic particle might be oriented in one direction or another. When you save a file, these tiny states take on specific patterns. When you delete a file, those patterns collapse into a standard default state. This collapse removes distinctions. Before deletion, there were many possible arrangements the memory could have been in. After deletion, there is only one. The device has lost the record of which pattern came before. The universe must absorb that loss by increasing disorder elsewhere. This connection between deletion and entropy comes from the fact that erasing information compresses many possible past states into a single present one. Imagine sorting a box of coins so that some show heads and others show tails. If you mix the coins randomly, the pattern is lost. You cannot look at the box and determine how many heads or tails were present originally. To lose that pattern is to increase disorder. In computers, the same thing happens when a memory cell is reset. The precise pattern of its earlier state is replaced with something simple and uniform. That simplicity hides a deeper cost. The information about the previous pattern has been spread into the environment, typically as waste heat. The physical world absorbs the erased details. This is why information loss is fundamentally one way. Once the details of a file are deleted, the system cannot jump back into the exact pattern that existed before without external input. The computer cannot spontaneously reassemble the data because the microscopic distinctions that defined the file have been scrambled into thermal motion. The information has not been destroyed in the sense of disappearing completely. The energy associated with erasing it has been released into the surroundings, but it has been dispersed into patterns that are impossible to gather again. Just like a cooling object cannot retrieve its radiated heat, a memory device cannot retrieve the scrambled distinctions that defined its previous contents. Even in natural systems, information behaves this way. When a message is whispered across a noisy room, subtle differences in tone and emphasis are lost in the background sound. When a wave crashes on a beach, the exact shape of the foam cannot be reconstructed from the swirling water that follows. When ink spreads through water, the precise droplets disappear forever into the mixture. These are all forms of information loss, where initial patterns dissolve into countless microscopic details. Reversing the process would require reconstructing every one of those tiny details, an impossibility without perfect knowledge of every motion and collision. In computation, there is a physical limit to how efficiently information can be processed. Every time a computer deletes a bit, turning a memory cell into a standard state, regardless of what it held before, it releases a minimum amount of energy as heat. This energy is tiny, far too small for a person to notice, but it accumulates in every device. Even the quiet warmth of a laptop or a phone is partly the result of countless tiny information erasing steps happening deep inside its circuits. The heating of a computer is not just an engineering issue. It is a direct expression of the connection between information and entropy. Because of this, many researchers dream of computers that could process information without erasing it, using reversible computing. In such a design, every step would preserve the information of the previous step, allowing the process to run backward in principle. But while this is theoretically possible, it is incredibly difficult in practice. Real-world systems are full of noise, imperfections, and thermal fluctuations that nudge them toward irreversibility. Even in the most careful designs, some information inevitably leaks away into the environment. The idea of a perfectly reversible computer is a beautiful concept, but the universe itself seems to encourage information to drift toward disorder. This tendency also shapes the limits of memory. No storage device can remember everything indefinitely. Over time, components age, magnetic orientations blur, charges leak, and tiny defects accumulate. The information that once existed becomes softer and eventually fades. This fading mirrors the psychological forgetting found in living beings, even though the mechanisms are completely different. Old memories drift into vagueness. Hard drives lose old data. Photographic film slowly degrades. Everywhere, information tends to dissolve into forms that can no longer be recovered without effort. A soft way to picture this process is to imagine writing in the sand near the shoreline. The pattern you draw, a word, a symbol, a design, is like stored information. The details of the pattern reflect deliberate choices. But as the tide rises and waves wash over the sand, the pattern begins to blur. The details soften. Eventually the water smooths the surface entirely. The sand is still there. The energy of the waves is still there. But the information that was encoded in the pattern has vanished, not because the sand has gone anywhere, but because the distinguishing features have been overwhelmed by the flow of countless grains and countless motions. To restore the pattern, you would need to rewrite it. The beach will not reconstruct it for you. Information loss also plays a huge role in how the universe evolves on large scales. When radiation spreads through space, it carries information about the objects that emitted it. As the universe expands, this radiation stretches and cools, losing clarity. Details about the early universe become increasingly blurred. The cosmic microwave background still carries the imprint of the universe's infancy, but its fine structure has been softened by billions of years of expansion. The original information has been diluted, spread across a volume far greater than the early cosmos ever occupied. This irreversible drift of information helps define the future. Once the universe loses track of certain details, it cannot spontaneously recover them. The arrow of time reflects this steady widening of possibilities. Ordered patterns dissolve into disordered ones. Distinctions blur. Memory, whether biological, digital, or cosmic, relies on delicate structures that degrade naturally unless effort is applied to maintain them. Yet there is something gentle about this story. Information does not vanish violently. It drifts away, it softens, it spreads. The universe forgets not because it is broken, but because forgetting is the natural consequence of countless tiny motions interacting across time. Everything that stores information, a brain, a computer, a stone, a star, participates in this quiet flow. And in that flow, the arrow of time becomes something deeply intuitive. Information moves from distinction to blending, from clarity to dispersion, from patterns to possibilities. The universe leans forward because forgetting is easier than remembering. And in the soft erosion of information, the direction of time becomes unmistakable. Every moment of your life depends on processes that quietly move in one direction. You breathe in air that mixes into your lungs and diffuses into your blood. You breathe out carbon dioxide that drifts into the atmosphere and will never unmix itself back into your bloodstream. You take in energy from food, use it to think and move, and release the leftover warmth into your surroundings. Every action, every thought, every heartbeat relies on irreversible flows woven through biology, chemistry, and physics. Without them, nothing familiar would work. Muscles would not contract, neurons would not fire. Even something as simple as warming your hands around a mug would behave differently. Life is built on the gentle truth that some things can only move forward. You can feel this directionality in the way your days unfold. Morning leads to afternoon, not the other way around. A memory forms after an experience, not before it. You grow older, not younger. Even routine tasks, drinking water, stepping outside, turning a page, opening a door, rely on tiny, irreversible steps. Water molecules disperse into new patterns. Air currents shift. Surfaces pick up microscopic traces of contact. None of these interactions ever reverse themselves completely. They take the world from one moment to the next, creating a flow that feels natural, almost invisible, yet profoundly important. Movement itself is an expression of irreversibility. Every time a muscle fiber contracts, chemical reactions inside your cells slide in one direction. These reactions liberate energy that cannot be fully recovered. Once the motion has happened, the cellular state is altered. You cannot unmove your hand by simply retracing every molecule's path. You can reverse the macroscopic movement, but not the microscopic details. They have already scattered into heat, vibration, and tiny chemical changes that drift deeper into the environment. This is why even a simple gesture carries the arrow of time quietly within it. Growth is the same. A plant stretching toward the light arranges its molecules in new, highly specific patterns. A child learning to read creates new pathways in the brain. These changes depend on energy flowing into organized states, and that energy is lost in ways that cannot be undone. You cannot reverse a day of growth the way you can reverse a step. The structure of a living system becomes more detailed, more shaped by experience with each passing moment. Even repairing damage, something life is remarkably good at, does not undo the original event. Healing produces a new configuration, not a rewind. Memory brings a different kind of one-way flow. You remember what has already happened because your brain has physically changed in response. Proteins have shifted, synapses have strengthened or weakened, and electrical patterns have altered the landscape of your mind. Forgetting too is a one-way path, not a reversal, but another forward step where the details soften and drift away. You cannot unform a memory in the exact opposite manner that you formed it. The tiny events that shaped it have already dissolved into newer neural patterns and scattered processes. The arrow of time is written into how you know yourself. Even the simple feeling of continuity, that one moment follows another, depends on irreversibility. If the world were perfectly reversible, nothing would distinguish past from future. You would have no sense of direction, no sense of after, no story of how you arrived at a moment. But because the world continually loses tiny bits of detail as events unfold, the past becomes something stable, something recorded in the patterns of matter and memory. The future stays open because it has not yet been written. This is why you can reflect on what has happened, but only imagine what will happen next. There is quiet comfort in this one-way flow. It means your life has structure. Morning routines feel reliable. Seasons progress in a steady rhythm. A warm drink cools. A breeze moves through the air. A heartbeat carries blood in one direction. Time's arrow gives these moments shape. Without irreversibility, the world would not be calmer or more predictable. It would be disorienting. Change would have no meaning. Cause and effect would blur. There would be no steady unfolding to guide you. Even the messy or fleeting parts of life gain softness through the forward movement of time. A difficult day does not loop indefinitely. A moment of frustration passes. A bruise fades. Sounds drift into silence. A scattering of leaves eventually settles. With each passing moment, the world takes the events of your life and blends them gently into memory, allowing you to move towards something new. The permanence of change is part of what allows you adapt, recover, learn, and continue. The broader world reflects the same pattern. Rivers carve deeper channels, winds shape dunes, oceans shift coasts grain by grain, stars shine and slowly cool. The universe itself expands, carrying galaxies farther apart in a steady outward drift. You live in a world where everything, from the smallest vibration of a particle to the largest sweep of cosmic structure, moves in this quiet forward direction. Your own internal sense of time is aligned with the universe's behavior, because at every scale, irreversibility gently guides the flow. This connection between the personal and the cosmic can feel unexpectedly grounding. The same principles that shape the cooling of stars help shape your memories. The same mathematics that guide the mixing of gases guide your breathing. Every irreversible process, whether in your own body or in the far reaches of space, is a reminder that the world knows how to move forward even when you do not have to think about it. You are carried along by a current that is calm, dependable, and universal. And as you move through your own life, the flow of time gives each moment a place. Things that have happened become part of your story. Things that have not happened remain possibilities. This is not a flaw or a limitation. It is what allows each day to be different from the ones before it. Irreversibility gives your life direction, depth, and meaning. Without it, everything would be frozen in endless symmetry. With it, you have a world that evolves, that remembers, that grows, and that gently leads you onward. In that way, your own experience as being alive is one of the clearest windows into the arrow of time. Every breath, every thought, every small act reflects the quiet truth that the universe moves forward. And in that steady direction, you find the rhythm that carries you toward whatever comes next. At the very beginning of the universe, long before stars formed or galaxies spiraled into existence, the cosmos took what you could think of as its first breath. It was a moment so brief and so distant that the human mind can only imagine its outlines, yet it shaped everything that followed. In that first instant, the universe was hot, dense, smooth, and remarkably organized. There were no galaxies, no clumps of matter, no swirling clouds or drifting clusters. Instead, everything was arranged in a state that was far more ordered than anything we see today. This astonishing orderliness is the quiet reason irreversibility exists at all. The universe began in a state with very few possible configurations, and from that point onward, it naturally drifted into states with more possibilities, more variety, and more complexity. That drift outward is what we experience as time. It might seem strange to think of the early universe as ordered. After all, a hot expanding plasma sounds chaotic. But the kind of order that matters here is not about neatness or quietness. It is about how many different ways the universe could have been arranged. In those first moments, matter and radiation were spread out almost perfectly evenly. There were tiny ripples, but nothing like the vast structures we see today. This uniformity is what made the early universe so special. Uniform states are surprisingly ordered because they limit the number of possible arrangements. A universe where everything is smooth has far fewer ways to be organized than a universe filled with stars, planets, galaxies, and life. Because of this early uniformity, the universe had a kind of stored potential. Not energy to spend, but complexity waiting to unfold. As the universe expanded and cooled, that potential began to express itself. Slight variations in density grew under gravity. Regions that were just a little more crowded pulled in more matter and became galaxies. Regions that were just a little emptier drifted toward becoming voids. The early universe's smoothness allowed these processes to begin. If everything had started already jumbled and irregular, the familiar structures of cosmic history might never have formed. This first low entropy state, this extraordinary initial order, created the arrow of time. Once the universe began moving away from that starting point, every new change had only one direction to travel, toward increasing disorder, increasing variety, and increasing numbers of possible arrangements. You can think of the early universe as being perched at the top of a slope, with all of history flowing downward, not in a falling sense, but in the sense of exploring the vast number of ways the cosmos could evolve. Galaxies forming, stars shining, planets cooling, life emerging. All of these are steps along the universe's long journey from its first breath to its present state. As the universe expanded, the energy that once burned fiercely in its earliest moments spread into larger and larger volumes. Radiation that started out blindingly bright stretched into the faint microwaves that fill the cosmos today. Matter that began smooth and uniform separated into the intricate cosmic web of galaxies and clusters. The early state of low entropy gradually became the complex high entropic universe you see when you look at the night sky. Every star, every swirling cloud, every glowing nebula is a sign that the universe moved forward from its starting point. None of these structures could ever form in reverse. There is no natural way to unwind these steps because the details have spread into countless tiny motions and patterns that cannot be traced back precisely. This long drift from order to complexity is not chaotic in a frightening sense. It is more like the unfolding of a story that has been waiting to be told. The early universe provided the opening line, a smooth, calm beginning, and everything afterward has been a natural elaboration. Stars condensed because gravity had the space to work. Planets formed because cooled matter could settle into disks. Life emerged because the chemical and physical conditions slowly became favourable. None of it had to be forced. It simply followed from the initial state and the rules of physics. When viewed with a gentle perspective, the idea that the universe began in such a special way becomes deeply calming. It means that time, direction, and change are not arbitrary. They are woven into the fabric of reality because the cosmos had a defined beginning with a well-organized shape. The universe did not start in confusion. It started with clarity, and everything since then has been the slow expansion of possibilities. Even the vast structures that exist today, the clusters of galaxies, the cosmic filaments, the enormous voids, carry echoes of that first low entropy moment. Their arrangement traces back to tiny fluctuations present in those earliest fractions of a second. those fluctuations grew and evolved into the cosmic landscape. They cannot be unwound because the universe has moved too far forward. The information needed to reverse them has been diluted, stretched, and scattered across billions of light years. In a sense, the universe remembers that early state by always drifting away from it. Every irreversible process you see, a cooling star, a mixing fluid, a fading heat source, or a growing tree, is a reflection of that original beginning. The arrow of time in your daily life is connected to the arrow of time on cosmic scales. The reason a warm drink cools, the reason memories form after experiences, and the reason galaxies drift apart are all linked to the fact that the universe once existed in a remarkably simple, uniform form. There is something peaceful in the idea that the entire universe shares this forward motion. Every part of reality, from the smallest particle to the largest supercluster, is moving together through time because of a single, elegant beginning. The early universe's low entropy did not just set the direction of time, it set the conditions that allow stars to shine, planets to orbit, and life to wonder about its place in the cosmos. And so, when you think about irreversibility, the way things only move forward, you can trace that feeling all the way back to the universe's first quiet breath. That breath defined the direction of everything that followed. Time's arrow began there, not with a violent shout but with a smooth, orderly opening, giving the cosmos room to unfold into the endless possibilities that now fill its vast expanse. Irreversibility has been the quiet thread running through every part of this journey, from the warmth that drifts away from stars and planets, to the mixing of colours, to the deep expansion of the universe itself. Everything you have explored has followed the same gentle pattern. Things spread, they blend, they cool, they soften, they drift into states with more possibilities than the ones before them. That simple movement, repeated everywhere, is what gives the world its sense of time and flow. It is what allows moments to unfold in order, one after another, without looping or repeating. It is what shapes the universe, and it is also what shapes you. Every breath you take follows this one-way tendency. The air enters your lungs, mingles with your blood, and releases its energy into the world. Every thought you have relies on chemical reactions that move in only one direction. Memories settle into place because tiny details inside your brain change, creating patterns that cannot be unwound. Even the warmth of your body, radiating gently outward, is part of this same quiet process. You're surrounded by a world that moves forward, and you are made of systems that do the same. All of this is rooted in something very simple and very deep. The universe prefers spreading to gathering, blending to unblending, unfolding to rewinding. Heat drifts toward the cold, structures slowly break down, light spreads into space, information softens and disperses. And somewhere within all of these movements, time becomes something you can feel. Morning follows night. Experiences settle into memory. Life carries you from one moment to the next. There is a calmness to this forward flow when you look at it closely. It means the world has rhythm. Events have meaning because they follow from what came before. A warm drink cools. A bright star dims. A planet slowly radiates away its ancient heat, and you move through your days with the same sense of continuity. You do not need to force anything to rewind or repeat. The universe gently carries you forward on its own, the same way it carries galaxies apart and sand grains down riverbeds. Irreversibility is not harsh or abrupt. It is smooth and patient. It is the soft mixing of clouds, the settling of dust, the fading of sound into silence. It is the quiet cooling of distant worlds and the long glow of aging stars. And it is the steady way your own memories and moments arrange themselves into the story of your life. Everything flows forward together because the universe began in a state so simple and ordered that moving into greater variety has been the natural direction ever since. From that first moment, the cosmos has been drifting outward, exploring possibilities, gently smoothing the edges of each new chapter. As you rest here now, you are part of that same unfolding. You're living in a universe that remembers its past only through the shapes it has grown into, and that moves into its future with a quiet, steady drift. Your thoughts, your experiences, your warm presence in this moment, all of them follow the same soft arrow of time. And in understanding how the universe moves, you may feel just a little more grounded within it. Thank you for spending this time here and for supporting the Sleepy Scientist. If you would like to help this channel grow, please consider leaving a like, subscribing, and clicking the notifications bell so you never miss an upload. It means more than you know, and it helps these calm journeys reach others who may need them. For now, let the world keep drifting forward on its gentle path. Let each thought soften, let each breath slow, and let yourself sink into the quiet flow of time, feeling the universe unwind into a peaceful night around you.